Beyond the familiar glow of our sun lie places in the universe that defy imagination, resembling more nightmares than reality. Picture worlds where rain is composed of sharp glass fragments, perpetual darkness shrouds the skies, or surfaces bubble with seething molten lava. These are not serene, dreamlike planets. They are the most daunting in the cosmos, where conditions are so severe that conventional life forms could not endure. The goal of this documentary is to push the boundaries of your understanding of the universe. Each planet we encounter will reveal the profound strangeness and terror that can exist in space. HD 189733b is a planet located 64.5 light-years away in the constellation Vulpecula. Known as a hot Jupiter due to its size and proximity to its star, it boasts extreme atmospheric conditions that challenge our understanding. One of its most striking features is its unique phenomenon of glass rain, which, despite sounding like science fiction, is scientifically verified. The planet's atmosphere is a turbulent inferno with temperatures surpassing 1,000 degrees Celsius, 1,832 degrees Fahrenheit, a result of its close orbit around its host star, subjecting it to intense stellar radiation. In this blazing environment, silicate particles are formed and remain molten in the atmosphere due to the extreme heat. Wind speeds on HD 189733b paint a dramatic contrast to Earth's weather systems. While hurricanes on our planet can reach speeds up to 250 kilometers per hour, 155 miles per hour, the winds on HD 189733b exceed a mind-boggling 7,000 kilometers per hour, 4,350 miles per hour, almost 20 times faster than Earth's most powerful hurricanes. To put this in perspective, these winds could cross the continental United States in less than 2 hours. These extreme conditions make HD 189733b a fascinating study, offering insights into planetary atmospheres and the astonishing forces at play beyond our solar system. The extraordinary wind speeds on HD 189733b are driven by the planet's close proximity to its star, which creates intense temperature differences across its atmosphere. This thermal imbalance propels hot air at tremendous speeds towards cooler regions, a phenomenon that defies comparison with anything on Earth. On this distant world, wind isn't just atmospheric movement. It shapes the planet's weather patterns and plays a crucial role in the surreal occurrence known as glass rain. Glass rain on HD 189733b is both fascinating and violent, profoundly influencing the planet's environment. Unlike Earth's gentle rains that nurture life, here molten silicate particles caught in the planet's fierce winds solidify into shards that pummel the surface at speeds up to 7,000 kilometers per hour, matching the velocity of the winds themselves. This relentless bombardment sculpts the planet's rugged terrain over vast timescales, potentially forming expansive, reflective dunes that glisten eerily under the nearby star's light. The implications of glass rain extend beyond physical surface alteration. The energy dynamics of this environment, fueled by the star's heat and kinetic energy from falling glass, sustain a volatile atmosphere unsuitable for liquid water, the cornerstone of life as we understand it. These extreme conditions pose significant challenges for identifying stable habitable zones on HD 189733b. Lately, I've been noticing that exploring the deep scientific concepts I cover started affecting my mental state. More specifically, after I made my video about universe mysteries that we can't comprehend. There were a few topics that made me feel really overwhelmed, and it started to weigh on me even after I finished editing in my office. Sometimes I find myself lying awake at night, replaying these ideas in my head, and it would sometimes lead to feeling anxious. It was like, the more I researched, the smaller and more insignificant everything seemed. There is no denying that feeling anxious or overthinking affects my ability to make interesting videos for you guys, especially considering that these long documentaries require a lot of work. For me, therapy would be very beneficial in processing these feelings. If you've been wanting to start your therapy journey, that's where BetterHelp, the sponsor of today's video, comes in. BetterHelp is an online therapy platform that connects you with a licensed therapist who is trained to listen and give you helpful, unbiased advice. First, you go to their site, answer a few questions, and BetterHelp will match you to a professional who has years of experience helping people with struggles just like yours. You can do it all from your phone or computer, via phone call, video chat, or messaging, however you feel most comfortable. It's the easiest possible way to start talking to a therapist. Let BetterHelp connect you to a therapist who can support you, all from the comfort of your own home. Visit betterhelp.com/spacedrift or choose Spacedrift during sign-up and enjoy a special discount on your first month. TRES 2b, an intriguing exoplanet located approximately 750 light-years away from Earth, holds the distinction of being the darkest planet known in the universe. This distant world reflects less than 1% of the sunlight it receives, making it darker than coal and a captivating subject for astronomers and scientists alike. The extreme darkness of TRES 2b is primarily due to its unique atmospheric composition and chemical processes, features that sharply contrast with the planets in our solar system. Its atmosphere is rich in light-absorbing chemicals such as vaporized sodium, potassium, and titanium oxide. Unlike in our solar system, where titanium oxide can reflect light and enhance brightness, the atmospheric conditions on TRES 2b prevent such reflection. Instead, these chemicals efficiently absorb almost all incoming sunlight, trapping it as heat and preventing any significant light reflection back into space. Additionally, there are indications that unidentified compounds in TRES 2b's atmosphere contribute to its high level of light absorption. Scientists continue to investigate the exact nature of these compounds. The planet's scorching temperatures, which can soar to around 1,000 degrees Celsius, 1,832 degrees Fahrenheit, also aid in maintaining its dark appearance by promoting chemical reactions that favor light absorption over reflection. The atmosphere of TRES 2b is believed to be rich in vaporized sodium and potassium, both known for their ability to absorb visible light. In the extreme heat of TRES 2b's environment, these elements prevent sunlight from being reflected back into space, contributing significantly to the planet's profound darkness. Additionally, titanium oxide, typically a light reflector in planetary atmospheres under the extreme conditions of TRES 2b, likely absorbs light instead of reflecting it, further intensifying the planet's dim appearance. Researchers also speculate about the presence of unidentified compounds in TRES 2b's atmosphere. These mysterious substances are thought to enhance the planet's light-absorbing capabilities, potentially revealing novel chemical processes occurring under the extreme temperatures and pressures unique to exoplanetary atmospheres. Kepler-70b, an exoplanet known for its extreme heat, challenges our understanding of planetary climates with its remarkable temperature range. Orbiting very close to its host star, Kepler-70, this planet experiences temperatures far surpassing those found on Earth or most other planets. Temperatures on Kepler-70b can range between 6,700 and 7,300 degrees Celsius, placing it among the hottest planets ever discovered. Its surface conditions resemble those found on the outer layers of stars rather than typical planetary atmospheres. The intense heat on Kepler-70b is primarily caused by its extremely close orbit around Kepler-70. This proximity exposes the planet to intense levels of stellar radiation, heating its surface to temperatures that vaporize metals and rock. This creates an environment that is incredibly harsh and almost unimaginably hot. Due to its tight orbit, Kepler-70b does not experience distinct day and night cycles, resulting in uniform temperatures across its surface that approach the limits of what solid matter can withstand before turning into plasma. Moving beyond the extreme temperatures of Kepler-70b, it is important to understand how its close proximity to its star profoundly influences its surface characteristics. The planet's surface is drastically different from any on Earth due to the intense stellar radiation it receives. This close relationship with Kepler-70 causes Kepler-70b's surface to reach temperatures where metals and rocks not only melt but vaporize, creating a landscape that is constantly changing. During its orbit, the extreme heat can form pools of liquid metals and silicates on the planet's surface, giving it a reflective appearance that contrasts sharply with Earth's familiar rocky or water-covered surfaces. The gravitational forces from its close orbit also subject Kepler-70b to significant tidal stresses, potentially leading to volcanic activity and unusual geological formations. This continuous activity contributes to a dynamic and ever-evolving world where even the ground beneath one's feet, if it were possible to stand there, is as transient as the atmosphere above. Kepler-70b's extreme conditions provide a profound example of the varied environments planets can endure. This diversity offers valuable insights into the processes governing planet formation and survival across the universe. For centuries, scientists have been fascinated by the intricate factors influencing planet formation, such as the composition of protoplanetary disks, distance from the host star, and the star's specific characteristics. Kepler-70b's existence in such an inhospitable region close to its star challenges established models of planet formation. It suggests that planets can form and maintain stability even in environments typically considered too extreme for such processes. This resilience hints that the mechanisms behind planet formation might be more adaptable and resilient than previously understood, capable of producing stable celestial bodies despite intense thermal and gravitational pressures. Studying Kepler-70b's extreme conditions also provides valuable insights into the later stages of planetary systems. As stars evolve and expand into their red giant phase, they can engulf their innermost planets, subjecting them to conditions akin to those experienced by Kepler-70b. This phenomenon underscores the dynamic nature of planetary systems and offers a glimpse into the fate of planets as their parent stars progress through their life cycles. Planet GJ 1214b, located about 40 light-years away, introduces a phenomenon that challenges our understanding of water in extreme environments. Classified as a super-Earth due to its size falling between Earth and gas giants, GJ 1214b hosts conditions leading to what's known as burning ice. This term describes a state of water existing under immense pressure and temperature conditions on the planet, conditions so extreme that they blur the boundaries between solid, liquid, and gas phases as we know them on Earth. The concept of burning ice on GJ 1214b arises from its dense atmosphere and potentially deep oceans. Under such high atmospheric pressure, water transforms into a supercritical fluid, a phase combining liquid-like properties such as solvent capabilities with gas-like behaviors such as filling containers uniformly. This supercritical water isn't ice in the traditional sense, nor does it burn in a fiery manner, but its existence under such extreme circumstances justifies the term. Burning ice. The planet's temperatures also play a crucial role in this phenomenon. Though not as searingly hot as some other exoplanets, GJ 1214b's temperatures are sufficient to prevent water from existing in a familiar liquid state at its surface, thereby fostering this exotic supercritical phase. This creates an environment where water behaves in ways entirely unlike anything observed on Earth, capable of dissolving materials like a liquid while freely moving and filling spaces like a gas. The pressure on GJ 1214b stands in stark contrast to the immense pressures found in Earth's deepest oceans, challenging our understanding of extreme environments. Earth's oceans reach their greatest depths in the Mariana Trench, where pressure reaches approximately 1,086 bars, or 15,750 pounds per square inch, psi. This pressure is akin to an elephant standing on a postage stamp, highlighting the intense conditions at such depths. However, GJ 1214b presents an entirely different level of pressure intensity. The planet's atmosphere is estimated to exert pressures thousands of times greater than the deepest ocean trench due to its larger mass, high density, and dense atmosphere, likely composed of heavy molecules. Under such extreme conditions, substances like water can exist in exotic states such as supercritical fluids, blurring the line between gases and liquids. Studying GJ 1214b poses unique challenges for scientists due to its intriguing characteristics and distant location. Situated about 40 light-years away, this exoplanet demands advanced telescopes equipped with highly sensitive instruments to analyze its atmospheric composition, temperature, and other critical features. Technological limitations and the vast distance from Earth complicate our efforts to gather and interpret data from such remote celestial bodies. Another significant challenge lies in the capabilities of current astronomical instruments. Despite considerable technological progress enabling us to observe distant planets more effectively, there are still constraints in resolving the intricate details of exoplanetary atmospheres. Specifically, identifying specific molecules or grasping the dynamics of atmospheric conditions remains challenging. This difficulty is exacerbated by the interference caused by the intense brightness of host stars, which often obscures or dilutes the signals emitted by these planets. This makes it challenging to extract precise characteristics of the planet from the mixed signals of reflected and emitted light. Furthermore, interpreting data from GJ 1214b is complicated by our limited understanding of how materials like supercritical fluids behave under the extreme pressures and temperatures found on such distant planets. Scientists heavily rely on theoretical models and laboratory experiments to simulate these conditions. However, these models have inherent limitations and cannot perfectly replicate the complex environments of exoplanets like GJ 1214b. Consequently, ongoing efforts are focused on refining these models and developing new techniques to enhance our understanding of the data gathered from observations of this intriguing exoplanet. WASP-12b, located about 600 light-years from Earth, has earned the moniker Doomed Planet, due to its exceptionally close orbit around its host star, a fate that has captured the interest of scientists and the public alike. This gas giant, comparable in size to Jupiter, is gradually being engulfed by its star, a dramatic example of the powerful forces shaping planetary destinies. The main reason for WASP-12b's doomed status stems from its extremely close proximity to WASP-12, its host star. This proximity subjects the planet to intense gravitational forces, resulting in it becoming tidally locked. This means one side of the planet always faces the star, while the other remains in perpetual darkness. The sun-facing side of WASP-12b experiences blistering temperatures exceeding 2,500 degrees Celsius, about 4,532 degrees Fahrenheit, causing its atmosphere to be stripped away into space. The star's gravitational pull has deformed WASP-12b into an elongated, egg-like shape, rather than the spherical shape typical of planets. This distortion vividly illustrates the star's profound influence on the planet. Observations reveal that WASP-12b is losing a substantial amount of mass, approximately 189 quadrillion tons per year, due to the star's heat and gravitational forces stripping away its outer layers, a phenomenon known as atmospheric escape. Scientists estimate that within a relatively short astronomical timeframe, possibly around 10 million years, WASP-12b may be completely consumed by its host star. This inevitability underscores the planet's doomed fate and underscores the dynamic and often violent nature of planetary systems. The study of WASP-12b and its inevitable demise provides profound insights into the planetary life cycle, particularly for planets in close orbits around their stars, showcasing the immense forces at work in our universe. Observations of WASP-12b's spiral towards its host star offer a captivating and somewhat foreboding view into celestial mechanics at their most extreme. Utilizing advanced telescopes and space-based observatories, astronomers have collected crucial data on this doomed planet, shedding light on the process of its consumption by the star. Astronomers have made compelling discoveries, notably detecting a vast cloud of material being drawn from WASP-12b towards its star due to the planet's close orbit and powerful gravitational forces. This material forms an extended atmosphere or exosphere, stretching from the planet towards the star, creating a bridge of gas gradually siphoned off WASP-12b. Spectroscopic analysis, a method to determine celestial object compositions by studying emitted or absorbed light, has played a pivotal role. Through spectroscopy, scientists have identified hydrogen, helium, and heavier elements among the gases in this stream, stripped from WASP-12b's atmosphere and assimilated into the star. Further observations reveal the staggering rate of mass loss, distorting WASP-12b's shape under the star's tidal forces into an elongated form. This distortion not only disrupts the planet's gravitational balance, but also accelerates atmospheric escape, hastening its demise. As WASP-12b sheds mass to its star, Significant changes occur in its atmosphere, with substantial quantities of gases, including hydrogen, helium, and heavier compounds, stripped away. The gradual stripping of WASP-12b's atmosphere leads to a reduction in atmospheric pressure, altering the delicate balance between the planet's surface and the vacuum of space. Enhanced by the intense heat from its nearby star, the remaining atmosphere expands and escapes more readily, hastening the loss. This atmospheric depletion can thin the protective layer around the planet, exposing its surface to harmful stellar radiation, potentially raising surface temperatures and even affecting the chemical composition of the surface itself. Additionally, the star's tidal forces elongate WASP-12b and can trigger geological activities like volcanic eruptions by heating the planet's interior. This geothermal activity might reshape the planet's surface over time, carving new features or altering existing ones. Studying WASP-12b's gradual demise not only provides insights into its inevitable fate, but also offers broader implications for understanding planetary evolution and the intricate interactions between stars and planets. These observations challenge previous assumptions about planetary orbit stability and the factors influencing planetary destruction. Transitioning from the dramatic case of WASP-12b, we encounter the intriguing scenario of HD 116906b, an exoplanet located approximately 300 light-years away from Earth. This planet's highly eccentric and distant orbit around its host star presents a stark departure from typical planetary systems. Positioned at a remarkable distance exceeding 650 times that between Earth and the Sun, HD 106906b resides in a region where traditional models of planet formation and orbital mechanics struggle to provide clear explanations. The disrupted orbit of HD 106906b prompts questions about the mechanisms that could have led to such an unconventional path. One prevailing theory suggests that gravitational interactions with other planets within its system, or possibly a passing star, could have profoundly altered its trajectory. Such interactions would need to be precisely orchestrated to place HD 106906b in its current orbit without ejecting it from the system or causing a collision with its host star. Another intriguing aspect of HD 106906b's orbit is its significant inclination relative to the plane of its solar system. This tilt adds to the mystery surrounding its origin and evolution, hinting at a potentially turbulent history within its planetary neighborhood that remains incompletely understood. The peculiar orbit of HD 106906b not only captures the interest of astronomers, but also challenges existing theories of planetary system formation. Traditional models focus on protoplanetary disks, dense gas and dust disks around young stars, as the cradle for planet formation, predicting planets to form within the disk and maintain orbits close to its plane, akin to our own solar system. However, the unique characteristics of HD 106906b suggest alternative mechanisms may influence the formation and evolution of planets in ways not fully accounted for by current models. One of the primary puzzles posed by HD 106906b's orbit is explaining how a planet ended up in such a wide and inclined trajectory, contrary to predictions from traditional formation mechanisms. This discrepancy suggests that additional factors beyond standard accretion and disk dynamics played significant roles. Theories propose scenarios involving gravitational disturbances from other massive bodies within the planetary system, such as giant planets, or close encounters with passing stars that could drastically alter a planet's path. These ideas imply a more tumultuous and dynamic early environment for the solar system than previously imagined. Moreover, the existence of HD 106906b challenges established notions about achieving and maintaining stable planetary orbits. Its current path indicates a potentially complex migratory history, possibly involving processes like planet-planet scattering or capture from another system. These mechanisms may contribute to the diversity of exoplanetary systems observed, extending beyond the orderly patterns found in our own solar system, expanding on the exploration of HD 106906b's unconventional orbit and its implications for traditional theories of planetary formation. we explore speculative yet intriguing possibilities for what may have shaped this exoplanet's extraordinary orbital characteristics. Unlike the familiar patterns seen in our solar system, HD 106906b's orbit suggests a backstory rich with celestial dynamics that challenge our understanding. A compelling hypothesis suggests that HD 106906b's orbit was influenced by gravitational interactions with another unseen companion within its system, potentially another planet or a brown dwarf. These interactions could have profoundly redirected HD 106906b early in the system's history, sending it into a distant and inclined orbit. This scenario hinges on a delicate balance of forces, ensuring that HD 106906b settled into its current wide orbit rather than being ejected entirely from the system. Another perspective on HD 106906b's perplexing orbit explores the possibility of a close encounter with a passing star during the early stages of its planetary system. This scenario suggests that within the dense environment of a star cluster, where stellar interactions are frequent, the gravitational influence of a nearby star could have profoundly disrupted HD 106906b's trajectory. Such an encounter could have altered the planet's velocity and direction, setting it on its current unusual path. Furthermore, the dynamics within the HD 106906 system itself during its formative years may provide additional insights into the origins of the planet's peculiar orbit. The phenomenon known as planet-planet scattering is proposed as a plausible mechanism. This process involves gravitational interactions among young planets within a forming system where planets can fling each other into different orbits. In the case of HD 106906b, planet-planet scattering could have propelled it into the wide and highly inclined orbit observed today. Coro 7b is an exoplanet situated 489 light-years away in the Monoceros constellation. What makes this planet particularly intriguing is its extreme environmental conditions, akin to rock showers. Orbiting its host star at a distance 23 times closer than Mercury orbits the Sun, Coro 7b experiences scorching temperatures on its dayside, reaching up to 2,500 degrees Celsius, 4,532 degrees Fahrenheit. Such intense heat causes rocks on its surface not just to melt, but to vaporize into gas, a phenomenon unseen on Earth. This vaporized rock is carried by the planet's atmosphere to its cooler night side, where temperatures drop significantly. Here, the rock vapor condenses into particles that eventually fall back as precipitation. This precipitation, however, isn't water but actual rock particles, a unique feature of Coro 7b. This cycle of vaporization and precipitation is a constant process driven by the stark temperature contrast between the planet's day and night sides. Additionally, Coro 7b's close proximity to its star causes intense gravitational forces that not only distort the planet's shape, but also affect its internal heating and atmospheric circulation. These forces contribute to the complex weather patterns observed on the planet, adding further intrigue to its study. The atmospheric phenomena observed on Coro 7b provide a unique glimpse into conditions vastly different from those found on Earth or within our solar system. On the planet's scorching day side, where temperatures reach up to 2,500 degrees Celsius, rocks vaporize into gas, which then cools and condenses on the cooler night side, forming rock rain. This extraordinary cycle offers scientists a live laboratory to study mineral and rock behavior under extreme conditions that cannot be replicated in terrestrial environments. Understanding how materials vaporize and condense on Coro 7b is crucial for refining models of planetary formation and evolution. These insights extend beyond exoplanets, potentially shedding light on Earth's geological history, atmospheric formation, and crust development. Moreover, studying Coro 7b's atmospheric dynamics helps scientists explore how extreme temperature gradients influence weather patterns and climate across different planetary settings, from scorching exoplanets to those more akin to Earth. This research challenges current theories about planetary habitability and expands our understanding of conditions that could support life elsewhere in the universe. By enhancing our knowledge of planetary diversity and evolution, researchers can better identify potentially habitable exoplanets and prioritize targets for future exploration. Scientists have been fascinated by 55 Cancri E, an exoplanet located 40 light-years away in the Cancer constellation and about twice the size of Earth, primarily because of its intriguing potential. It may possess a surface abundant in diamonds. This hypothesis arises from the planet's unique composition and the extreme pressure conditions it sustains. Unlike Earth, which has a rocky surface, 55 Cancri E is predominantly made of carbon in forms such as graphite and potentially diamond. The transformation of carbon into diamond on 55 Cancri E begins deep within the planet, where temperatures are sufficient to melt carbon. Under the immense gravitational pressure of the planet, molten carbon gradually crystallizes into diamond. This process mirrors diamond formation on Earth, but occurs on a larger scale and at much higher temperatures. On our planet, diamonds form deep below the surface over billions of years under high temperature and pressure conditions, typically around 150 kilometers below ground. Conversely, on 55 Cancri E, this process is accelerated by the planet's extreme environment, potentially resulting in a surface layer largely composed of diamond. This hypothesis is bolstered by observations of 55 Cancri E's density and its parent star's carbon-rich nature. The planet's exceptionally high density indicates it is not composed of lighter elements like hydrogen and helium, as seen in many gas giants, but instead of heavier elements such as carbon. Coupled with the carbon abundance observed in its star, scientists posit that 55 Cancri E might indeed be a diamond world. The discovery of valuable materials like diamonds on planets such as 55 Cancri E provides profound insights into the diverse processes of planet formation and the varying conditions found across our universe. This revelation highlights the vast range of compositions and characteristics that planets can exhibit, illustrating the incredible diversity of planetary systems beyond our own. This diversity stems from the availability of materials in the regions where planets form around their host stars. For instance, 55 Cancri E's abundance of carbon, relative to other elements, suggests that its formation region was enriched in carbon-based compounds. This is in contrast to Earth, where silicon and oxygen predominate, resulting in a rocky surface. The presence of a diamond-rich planet indicates that the protoplanetary disk from which it originated had a distinct chemical composition, underscoring the influence of stellar and molecular cloud environments on shaping emerging planets. The transformation of these materials under extreme conditions, such as high pressure and temperature leading to diamond formation, provides valuable insights into the internal processes and thermal dynamics of these distant worlds. It implies that planets can possess internal heat and pressure mechanisms vastly different from those found on Earth, opening new avenues for research in planetary geophysics and chemistry. Understanding how planets with surfaces rich in valuable materials form also enhances our knowledge of the life cycles of stars and planetary systems. It hints at the evolutionary trajectories that planetary systems might follow and the long-term fate of planets over billions of years. For example, a planet rich in carbon may evolve differently over time compared to a planet abundant in water or a gas giant, influencing its surface conditions, atmosphere, and potential to harbor diverse forms of life. The rings of J1407b, an exoplanet located hundreds of light-years away from Earth, represent a breathtaking discovery in the field of exoplanetary science. These rings are not only expansive but also extraordinarily vast, surpassing anything found within our own solar system. To grasp their scale, consider that J1407b's rings are so immense that they could encircle Saturn's rings over 200 times. Saturn's rings, already a wonder of our solar system, pale in comparison to the sheer size of J1407b's ring system. Spanning nearly 90 million kilometers, about 56 million miles in diameter, J1407b's rings highlight the remarkable diversity of planetary systems across the universe. Their discovery provides astronomers with a captivating opportunity to study planetary formation dynamics and the complexities of ring systems. composed of ice, rock particles, and possibly moonlets or smaller bodies orbiting the planet, similar to Saturn's shepherd moons. These rings offer clues about the planet's past. The colossal expanse of J1407b's rings suggests they could be remnants of a colossal collision or the early stages of moon formation, offering insights into processes that may have occurred during the early solar system, but on a much larger scale. Analogous to Saturn's rings, which have demonstrated how moons can form within a planet's ring system, the particles within J1407b's rings interact under the planet's gravitational influence, potentially forming moonlets that could evolve into larger moons over time. The theory suggests that as particles within J1407b's vast rings collide and adhere to one another, they gradually aggregate into larger objects over time. These growing objects may eventually accrue enough mass to clear their orbits within the ring, a crucial step in their transformation into fully formed moons. This intricate process, though gradual and complex, provides a compelling window into planetary science, offering insights into the potential formation mechanisms of moons and other small bodies within our solar system. The emergence of moons within the expansive rings of J1407b holds profound implications for our comprehension of planetary systems and the dynamics of ring structures. Studying this phenomenon provides valuable opportunities to gather data on the conditions conducive to moon formation, the timelines involved in this evolutionary process, and how newly formed moons might influence the overall structure and stability of their parent rings. Ogle 2005 BLG 390 LB, located approximately 21,500 light-years away in the constellation of Sagittarius, has earned the classification of an ice-ball planet due to its frigid surface temperatures and distant orbit from its parent star. This distant positioning places it far beyond Earth's distance from the Sun, resulting in minimal warmth reaching the planet. Described as an ice ball, Ogle 2005 BLG 390 LB exhibits surface temperatures estimated around -220 degrees Celsius, -364 degrees Fahrenheit, cold enough to keep water permanently frozen across its entire landscape. This characterization stems from its thermal properties and environmental conditions. Unlike ice giants in our solar system, such as Uranus and Neptune, which possess thick atmospheres rich in hydrogen and helium, an ice ball planet like Ogle 2005 BLG 390 LB is believed to feature a solid, icy surface. Its extreme cold is primarily due to its distant orbit, which limits the amount of solar energy it receives, preventing its surface from warming above the freezing point of water. This classification underscores the vast range of planetary environments present in our universe. Ice ball planets challenge our notions of habitability and the conditions necessary for life. While the severe cold on such planets seems inhospitable to life as we understand it, studying these celestial bodies provides valuable insights into the extreme climates that can exist on planets and their potential for hosting water in its various forms across different cosmic bodies. In planetary science, a planet's temperature is a critical factor shaping its atmosphere. Ogle 2005 BLG 390 LB, being extremely cold, faces unique atmospheric challenges. Volatile compounds like water vapor, carbon dioxide, and methane, which would normally form gases on warmer planets, freeze out on its surface as snow or ice. This process significantly thins and reduces the density of its atmosphere, as fewer gases remain in a vapor state to create a substantial atmospheric layer. The lack of a thick atmosphere on Ogle 2005 BLE 390 LB means that any heat from its star or internal sources is not effectively retained, intensifying its already cold conditions. In contrast, planets with thicker atmospheres, rich in greenhouse gases, can trap heat and maintain relatively warmer temperatures, even at great distances from their stars. The temperature and atmospheric conditions of Ogle 2005 BBLG 390 LB provide insights into its potential to support life as we understand it. The absence of a substantial atmosphere and the extreme cold make it unlikely for liquid water to exist on its surface, a crucial requirement for life as we know it on Earth. However, These harsh conditions spark curiosity about the possibility of extremophile life forms adapted to such extreme environments, challenging our understanding of habitability in the universe. Researching distant and cold planets like Ogle 2005 BLG 390 LB, located thousands of light-years away, involves advanced astronomical techniques and technologies. Scientists utilize observational methods and theoretical models to unravel the mysteries of these distant worlds. Gravitational microlensing is a key technique used to detect and study planets like Ogle 2005 BLG 390 LB. This phenomenon occurs when the gravity of a foreground star or planet bends and magnifies the light from a background star, revealing the presence of planets orbiting the foreground star and providing details about their mass and distance from their host star. Gravitational microlensing is a powerful method for detecting distant and faint exoplanets that are difficult to observe using traditional techniques like transit observations or direct imaging. This method is particularly effective for finding cold iceball planets such as Ogle 2005 BLG 390 LB. Unlike other methods, microlensing does not rely on the planet or its host star emitting light. Instead, it detects planets by observing how their gravity bends and magnifies the light from a background star. This approach is highly sensitive to low-mass planets and can detect them across a wide range of distances from their host stars. In conjunction with gravitational microlensing, scientists employ sophisticated computer models and simulations to study these distant planets. By inputting known physical parameters such as the planet's mass, distance from its star, and orbital characteristics, researchers can simulate conditions on the planet's surface and atmosphere. These models provide valuable insights into the planet's temperature, atmospheric composition, and potential for hosting water or ice. To confirm and further investigate microlensing detections, telescopes equipped with sensitive instruments, both on the ground and in space, are essential. These telescopes gather additional data about the star system, refining measurements and validating the presence of the detected planet. While directly observing the atmosphere or surface of such distant planets remains challenging, the combined use of microlensing and follow-up observations offers scientists significant knowledge about these remote celestial bodies. Kelt 9b holds the distinction of being the hottest known exoplanet, owing to a combination of extreme factors that create its blistering conditions. Situated approximately 670 light-years away in the constellation Cygnus, Kelt 9b orbits its host star Kelt 9, which is exceptionally hot, nearly twice as hot as our Sun. This stellar proximity is key, with Kelt 9b completing an orbit in just about 1.5 Earth days, placing it in a tremendously close and intense stellar environment. Due to its close orbit around Kelt 9, Kelt 9b receives thousands of times more radiation than planets in our solar system receive from the Sun. This intense radiation heats the planet's atmosphere to over 4,300 degrees Celsius, 7,800 degrees Fahrenheit, hotter than many stars and well beyond the melting points of most materials found on Earth. These extreme temperatures foster unique atmospheric chemistry, potentially leading to vaporized metals and the destruction of molecular hydrogen, typically abundant in other gas giants' atmospheres. Additionally, Kelt 9b lacks a significant reflective atmosphere that could moderate its temperatures. The absence of reflective clouds or ice allows the planet to absorb a maximum amount of stellar radiation, further elevating its already scorching surface temperatures. The planet's tidally locked rotation, where one side always faces the star and the other remains in perpetual darkness, exacerbates these extremes. Despite potential heat distribution by atmospheric winds, the day side of Kelt 9b remains infernally hot, providing a striking example of the extreme conditions that exoplanets can experience. For Kelt 9b, the hottest known exoplanet, upcoming observations aim to delve deeper into its remarkable atmosphere and the extreme conditions created by its proximity to its host star, Kelt 9. Astronomers are eager to leverage the next generation of space and ground-based telescopes to explore this intriguing world in greater detail. A primary objective is to scrutinize Kelt 9b's atmospheric composition, particularly identifying exotic molecules and vaporized metals that exist due to its scorching temperatures. substances that may be rare or unknown in cooler planetary atmospheres. Another critical focus of future observations is investigating Kelt 9b's atmospheric dynamics and weather patterns. The stark temperature contrasts between its day and night sides present an opportunity to uncover unprecedented insights into extreme weather phenomena, potentially unlike anything observed in our solar system. Advanced instruments such as the James Webb Space Telescope, JWST, and the Extremely Large Telescope, ELT, are poised to play pivotal roles in these endeavors. The JWST's infrared sensitivity will enable detailed measurements of Kelt 9b's thermal emissions, offering crucial data on temperature distribution and atmospheric makeup. Meanwhile, the ELT's superior resolution will provide unprecedented views of the planet's atmospheric chemistry. Additionally, future observations will seek to investigate Kelt 9b's magnetic field and its interaction with the stellar wind from Kelt 9. Understanding this interaction is essential for comprehending atmospheric loss processes and their impact on the planet's long-term evolution and stability. The extreme seasonal variations on HD 80606b, a gas giant exoplanet located approximately 190 light-years away in the constellation Ursa Major, stem from its highly eccentric orbit around its host star. Unlike the nearly circular orbits of planets in our solar system, HD 80606b follows a highly elongated path that brings it very close to its star at periastron, the closest point in its orbit, and then swings it far away at apastron, the farthest point. This unique orbital setup results in dramatic fluctuations in temperature and weather patterns on the planet throughout its orbit, which lasts about 111 days. During periastron, when HD 80606b approaches its star closely, it undergoes rapid and extreme heating due to intense solar radiation. Within hours, the planet's atmosphere can heat up by hundreds of degrees, a phenomenon unseen in our solar system. This rapid temperature increase drives powerful weather phenomena like supersonic winds and expansive storm systems that can envelop the entire planet. This contrasts sharply with the much cooler and calmer conditions experienced at apastron, when HD 80606b is farthest from its star. The degree of these seasonal changes is further influenced by the planet's rotation and its orbital tilt. If HD 80606b is tidally locked, with one side permanently facing the star, the contrast between its scorching day side and frigid night side would be accentuated. However, even if the planet rotates, the swift heating and cooling as it traverses its eccentric orbit would still lead to significant seasonal variations. Astronomers employ diverse methods such as transit observations and radial velocity measurements to study the extreme seasonal variations of HD 80606b. These techniques involve observing the planet as it passes in front of its star from our viewpoint and monitoring the star's motion caused by the planet's gravitational pull. Through these observations, scientists gain insights into the dynamics of HD 80606b's atmosphere and how its eccentric orbit influences its climate. The pronounced seasonal changes on HD 80606b, driven by its highly eccentric orbit, hold significant implications for its potential habitability. The planet experiences dramatic shifts in temperature and weather conditions, ranging from extreme heat to relatively cooler phases, which present challenges for the emergence and sustainability of life as we know it. During periastron, the planet's closest approach to its star, the atmosphere can rapidly heat up by hundreds of degrees in mere hours, creating harsh conditions unsuitable for life. Habitability typically hinges on a stable environment where liquid water can persist on a planet's surface, an essential condition for life. However, on HD 80606b, the extreme temperature swings make it unlikely for liquid water to remain stable. Near periastron, any surface water would likely evaporate due to the intense heat, while at apastron, the coldest point in its orbit, any remaining water could freeze solid. The planets circling the pulsar PSRB 1257+12 present a fascinating and unexpected find in astronomy, challenging our notions of planetary formation. Pulsars are neutron stars with intense magnetic fields that emit electromagnetic radiation from their poles as they spin. This radiation sweeps past Earth like a beacon detectable by radio telescopes. Located approximately 2,300 light-years away in the Virgo constellation, PSRB 1257 plus 12. Stunned astronomers by hosting planets. This discovery was groundbreaking because it showcased planets existing in a vastly different setting compared to our solar system. What sets these planets apart is not just their orbit around a pulsar, but also the unique conditions they endure. Pulsars are the remnants of massive stars that have undergone supernova explosions, leaving behind an incredibly dense core composed mainly of neutrons. These neutron stars possess intense magnetic fields and emit high levels of radiation, creating an extremely harsh environment unsuitable for life as we know it. The discovery of planets around pulsars poses intriguing questions about how these planets formed and continue to exist. Traditional theories of planet formation, which involve the gradual accumulation of dust and gas in a protoplanetary disk around a young star, don't straightforwardly apply to the surroundings of a neutron star. Such material would likely have been dispersed by the supernova explosion that formed the pulsar. The planets orbiting PSRB 1257 plus 12 were first identified in the early 1990s and are primarily terrestrial in mass. Their detection marked a significant advancement in exoplanetary science, achieved through precise measurements of the pulsar's pulse timing. As these planets orbit the pulsar, their gravitational influence causes slight variations in the timing of its pulses, a unique method for detecting exoplanets associated with pulsars. The formation of these pulsar planets presents another fascinating puzzle. One hypothesis proposes that they could have originated from the debris left behind by the supernova, indicating a potential second round of planet formation. Alternatively, these planets might have been pre-existing bodies captured by the pulsar's gravitational pull or remnants of a star system that managed to survive the supernova explosion in some capacity. The discovery of planets orbiting PSRB 1257 plus 12 marked a significant breakthrough in exoplanetary research, demonstrating that planets can form and endure in extreme and previously thought inhospitable environments. The conditions on these pulsar-orbiting planets stand in stark contrast to those found in our solar system, presenting an environment that is nearly unparalleled. Our solar system's planets orbit a stable main sequence star, the Sun, which provides a steady source of light and heat crucial for sustaining life on Earth and influencing the climate and atmospheric processes on other planets. In contrast, the planets orbiting PSRB 1257 plus 12 circle. A pulsar, an extraordinarily dense remnant of a supernova explosion emitting intense electromagnetic radiation and possessing formidable magnetic fields. The radiation environment surrounding a pulsar is exceedingly harsh compared to the sunlight that bathes our solar system. Pulsar radiation can strip away atmospheres, irradiate surfaces, and potentially sterilize planets, rendering them inhospitable for life as we understand it. In our solar system, planets like Earth benefit from protective magnetic fields that shield them from solar wind and cosmic rays, safeguarding their atmospheres and enabling conditions conducive to life. Conversely, the planets orbiting PSRB 1257 plus 12 lack such protection, suggesting any atmosphere they may possess could be minimal or absent altogether. The process of planet formation around a pulsar differs significantly from that in our solar system. While our solar system's planets coalesced from a protoplanetary disk of gas and dust surrounding the young Sun, the planets around PSRB 1257 plus 12 likely formed from the remnants of the supernova that produced the pulsar. This suggests a distinct second phase of planet formation, potentially involving different materials and mechanisms compared to those that shaped our solar system's planets. Temperature conditions also illustrate a striking contrast. In our solar system, planets experience temperatures suitable for liquid water on Earth and icy environments on outer planets, driven by the Sun's consistent energy output. In contrast, planets orbiting PSRB 1257 plus 12 likely endure extreme temperature fluctuations influenced by their proximity to the pulsar and its intense emissions. These conditions diverge significantly from the stable environments observed in our solar system, where varying climates and atmospheric dynamics are supported by the Sun's radiation. Corot 2b, an exoplanet discovered by the Corot space mission, provides a compelling example of a planet influencing its host star in observable ways from Earth. This hot Jupiter orbits Corot 2 every 1.7 days, positioned very close to its star. This close proximity results in significant interactions between the planet and its host star, revealing dynamic processes between stars and their planets. One notable effect of Corot 2b on its host star is star-planet interaction. The strong gravitational pull of Corot 2b can trigger activity in the star's outer layers, potentially increasing magnetic activity such as star spots and flares. This phenomenon draws parallels to how the Moon affects Earth's tides, but operates on a larger scale, involving magnetic fields and stellar plasma. The close orbit of Corot 2b around its host star exposes it to intense stellar radiation, heating the planet's atmosphere to extreme temperatures. This thermal energy can cause the planet's atmosphere to expand and sometimes escape into space. As the atmosphere escapes, it forms a cloud of material around the planet that interacts with the star. This interaction can lead to a transfer of angular momentum from the planet to the star, influencing the star's rotation rate and magnetic field. The Corot 2 system presents another fascinating dimension: the potential for the planet to induce chemical changes in its host star's outer layers. As material from Corot 2b's atmosphere escapes, it may accrete onto the star, altering its chemical composition and spectral characteristics. This process, called accretion, allows astronomers to infer details about the planet's atmosphere by studying changes in the star's spectrum. Astronomers employ spectroscopy to examine these interactions, analyzing the star's light to detect variations in brightness, magnetic activity, and chemical makeup. Observations of the Corot 2 system contribute significantly to our understanding of how planets influence their host stars, providing insights into the evolution of planetary systems and the intricate dynamics that govern their interactions. The interaction between Corot 2b and its host star, Corot 2a, underscores the complex relationships between stars and planets, expanding our comprehension of the cosmic interplay throughout the universe. These interactions demonstrate that planets, particularly those in close orbits like hot Jupiter's, can profoundly impact their stars, influencing magnetic behavior, rotation rates, and even the chemical compositions of their host stars. This perspective contrasts sharply with the traditional belief that stars unilaterally determine the conditions of their orbiting planets without reciprocal effects. The phenomenon of star-planet interaction, exemplified by the Corot 2 system, reveals that planets can induce magnetic disturbances in their host stars, triggering heightened stellar activity like flares and spots. This discovery is significant because it suggests that planets' presence and characteristics can directly influence the stellar environment, altering the conditions that govern these celestial bodies' existence and evolution. In the case of Corot 2b, its close orbit around the host star and the resulting gravitational forces illustrate how a planet's influence can extend beyond its own atmosphere, impacting the star itself. These interactions underscore the potential for atmospheric loss from planets exposed to intense stellar radiation. The process of a planet losing its atmosphere and potentially transferring material to the star establishes a mutual exchange between stars and planets, blurring the boundaries of their relationships. This exchange can lead to changes in the chemical composition of the star's outer layers, offering astronomers indirect means to study exoplanet atmospheres through observations of their host stars. The intriguing phenomenon of gemstone rain on HAT P7b, an exoplanet located approximately 1,040 light-years away, highlights its unique atmospheric dynamics shaped by extreme conditions on this gas giant. HAT P7b belongs to the category of hot Jupiters, similar in size to Jupiter but much closer to its host star, resulting in extraordinarily high temperatures. The precipitation of materials like rubies and sapphires in its atmosphere is attributed to the presence of aluminum oxide. Under terrestrial conditions, aluminum oxide crystallizes into corundum, the mineral base for gems such as rubies and sapphires, depending on trace impurities. The scorching temperatures on HAT P7b's day side facilitate the formation of aluminum oxide vapor in its atmosphere. Orbiting so close to its star subjects the planet to intense stellar radiation, heating the atmosphere to temperatures where metals can vaporize and chemical reactions can occur. As the vapor moves with strong winds to the cooler night side, the temperature drop allows the aluminum oxide to condense into clouds. Further cooling may lead to the precipitation of corundum crystals, which could resemble rubies and sapphires depending on local conditions, such as the presence of trace elements like chromium or iron. This phenomenon poetically describes gemstone rain on HAT P7b. This extraordinary weather phenomenon underscores the fascination of studying exoplanets, offering insights into the diverse environmental conditions beyond our solar system. Researchers study HAT P7b's atmospheric dynamics, including gemstone rain, through variations in its brightness and spectral analysis. These observations reveal details about the planet's atmospheric composition and temperature distribution, advancing our understanding of planetary science and the complexities of hot Jupiter climates. The remarkable occurrence of iron rain on WASP 76b, situated approximately 640 light-years away in the Pisces constellation, arises from the extreme temperature differentials and unique atmospheric dynamics of this ultra-hot Jupiter. WASP 76b orbits very close to its host star, completing an orbit in just 1.8 Earth days, exposing its day side to intense stellar radiation. Daytime temperatures exceed 2,400 degrees Celsius, about 4,350 degrees Fahrenheit, sufficient to vaporize metals like iron. The process of iron rain begins with iron vaporizing on the scorching day side of the planet. This vapor is then transported by atmospheric currents to the cooler night side, where temperatures drop significantly. As the vapor cools, it condenses into droplets, forming clouds that precipitate as iron rain. This stark temperature disparity between the day and night sides, coupled with efficient atmospheric circulation, creates the ideal conditions for this metallic precipitation. Studies of WASP 76b, particularly using spectroscopy, have confirmed this phenomenon. Spectroscopic analysis enables astronomers to identify the chemical compositions of planetary atmospheres by examining the starlight filtered through them. The presence of iron vapor on the day side and its absence on the night side indicates that the iron condenses and precipitates as rain before it can cycle back to the day side. TOI 700D, discovered by NASA's TESS mission, has drawn significant interest from scientists and space enthusiasts alike due to its potential habitability. Situated approximately 100 light-years away in the Dorado constellation, TOI 700D orbits a small, cool M-dwarf star as the outermost planet in its system. What distinguishes TOI 700D as a promising candidate for habitability are several key characteristics, setting it apart from many other exoplanets. Crucially, TOI 700D resides within its star's habitable zone, an orbital region where conditions may be conducive for liquid water to exist on the planet's surface, a fundamental prerequisite for life as we understand it. Its orbit places it at a distance where it receives a comparable amount of stellar energy as Earth does from the Sun, implying temperatures on TOI 700D could support liquid water, given the presence of an appropriate atmosphere. Moreover, TOI 700D is roughly Earth-sized, with estimates suggesting it has a radius about 1.2 times that of Earth. This similarity in size suggests a rocky composition akin to Earth, Mars, and Venus, enhancing its potential to maintain a stable atmosphere, a critical factor for habitability. An atmosphere could not only supply essential gases for life, but also regulate the planet's temperature by trapping heat through greenhouse effects. TOI 700D's orbit is tidally locked to its star, resulting in one side of the planet always facing the star, the day side, while the other side remains in perpetual darkness, the night side. This arrangement, typically leads to drastic temperature differences between the two hemispheres. However, the presence of an atmosphere could mitigate these extremes by redistributing heat, potentially stabilizing the climate enough to sustain liquid water and possibly life. TOI 700, the host star of TOI 700d, belongs to the category of quiet M dwarfs, known for exhibiting fewer solar flares compared to other stars of similar type. Solar flares can erode a planet's atmosphere and subject its surface to harmful radiation, factors that can hinder habitability. The relatively tranquil behavior of TOI 700 enhances the prospects for TOI 700d's habitability by reducing these risks. LHS 3844b, an exoplanet orbiting a red dwarf star about 48.6 light-years away in the constellation of Indus, exhibits extreme temperature disparities between its day and night sides due to its close proximity to its host star and its apparent lack of a substantial atmosphere. This terrestrial planet completes an orbit around its star in just 11 hours, positioning it much closer than Earth is to the Sun. This proximity results in the planet receiving intense stellar radiation on its day side, leading to extremely high temperatures. The primary factor driving the stark temperature contrast on LHS 3844b is its tidally locked orbit. Tidal locking means one side of the planet always faces the star, experiencing perpetual daylight, while the opposite side remains in continuous darkness. In the absence of an atmosphere to redistribute heat, the day side becomes intensely hot, while the night side remains significantly cooler due to the absence of direct stellar heating. Studies using instruments like NASA's Spitzer Space Telescope suggest that LHS 3844b likely lacks a substantial atmosphere. An atmosphere plays a crucial role in regulating a planet's climate by distributing heat. For instance, Earth's atmosphere helps moderate global temperatures by transferring heat from equatorial regions to the poles. The absence of such an atmosphere on LHS 3844b means that heat from its star isn't effectively distributed across the planet. Consequently, temperatures on the day side of LHS 3844b can soar to around 800 degrees Celsius, approximately 1,472 degrees Fahrenheit, while the night side experiences a substantial drop in temperature due to the lack of direct sunlight. Gliese 1214b is classified as a super-Earth because it is an exoplanet larger than Earth, but smaller than the ice giants Uranus and Neptune. It possesses a mass about 6.5 times that of Earth and a radius approximately 2.7 times larger, placing it squarely within the category of super-Earths. The significance of this classification lies in the range of potential characteristics Gliese 1214b could exhibit, including a dense atmosphere, the presence of liquid water, or even an ocean-dominated surface, depending on its composition and atmospheric conditions. However, the term super-Earth does not imply that the planet is necessarily habitable or Earth-like in terms of its climate and environment. Rather, it denotes its size relative to Earth and suggests a diversity of planetary types beyond our solar system. Super-Earths like Gliese 1214b captivate astronomers because they represent a planetary class absent in our own solar system. They offer unique opportunities to study planetary formation, evolution, and the potential for life under conditions distinct from those found on Earth. Gliese 1214b orbits a red dwarf star located approximately 48 light-years away in the constellation Ophiuchus. Its close proximity to its host star, resulting in a short orbital period of about 38 hours, significantly influences the planet's temperature and atmospheric dynamics. Observations indicate that Gliese 1214b possesses a substantial atmosphere, potentially rich in water vapor or other heavy molecules. This characteristic has sparked interest in understanding its surface conditions, including the possibility of hosting an exotic form of water under extreme pressure and temperature, a concept known as a water world. Studying Gliese 1214b alongside other super-Earths is pivotal for advancing our understanding of the diverse array of planets throughout the cosmos. Scientists employ sophisticated techniques such as transit spectroscopy to analyze the atmospheres of these distant worlds. This method provides valuable insights into their chemical compositions, weather patterns, and the potential suitability for life as we know it. Such research not only expands our knowledge of exoplanetary systems, but also refines models of planetary formation under diverse environmental conditions. Proxima Centauri b orbits the closest star to the Sun, Proxima Centauri, located approximately 4.2 light-years away in the constellation of Centaurus. It stands out as a leading candidate in the search for extraterrestrial life due to several compelling attributes. Chief among these is its position within the habitable zone of its star, often referred to as the Goldilocks zone. This zone denotes the range of distances from a star, where conditions could potentially support liquid water on a planet's surface, a crucial requirement for life as we understand it. Proxima Centauri b's orbit within this zone suggests it could maintain surface temperatures conducive to liquid water, provided it possesses a suitable atmosphere. Another key factor supporting Proxima Centauri b's candidacy for hosting life is its Earth-like size. Estimates indicate the planet is at least 1.17 times the mass of Earth, indicating a rocky composition rather than a gaseous one. This similarity in size and composition increases the likelihood that Proxima Centauri b may harbor Earth-like environmental conditions, further bolstering its potential for habitability. The planet's proximity to Earth presents a unique advantage for scientific observation and study. As the closest known exoplanet, Proxima Centauri b is a prime target for future missions and telescopes designed to examine exoplanetary atmospheres, surface features, and potential signs of life. Advanced technologies, including upcoming instruments like the James Webb Space Telescope, offer the promise of analyzing the planet's atmospheric chemistry, searching for water, and detecting molecules that could hint at biological activity. While Proxima Centauri b holds promise as a potential haven for extraterrestrial life, there are notable challenges to its habitability. Orbiting Proxima Centauri, a red dwarf star known for frequent stellar flares and high levels of activity, the planet faces significant radiation exposure. These factors could jeopardize its atmosphere and surface conditions, essential for supporting life as we understand it. For Proxima Centauri b to sustain life, it would likely require a robust magnetic field capable of shielding it from the star's intense radiation and preserving its atmosphere. Despite these challenges, Proxima Centauri b remains a leading candidate in the search for alien life due to its placement within the habitable zone of its star, its Earth-like size, and its status as the closest exoplanet to our solar system. Scientists are eager to explore Proxima Centauri b further through future observations, which could provide crucial insights into its potential for hosting life beyond Earth. Kepler-22b, discovered by NASA's Kepler Space Telescope, has captured significant attention within the scientific community for its potential to support life. Positioned approximately 620 light-years away in the constellation of Cygnus, this exoplanet orbits within the habitable zone of its star, Kepler-22. This zone is crucial because it encompasses distances where conditions might permit liquid water to exist, a fundamental requirement for life as we understand it. The primary allure of Kepler-22b lies in its location within this habitable zone. This positioning suggests that the planet receives a comparable amount of stellar radiation to Earth from the Sun, potentially fostering a climate suitable for liquid water on its surface. Liquid water is vital for biochemical processes essential to sustain life. Moreover, Kepler-22b boasts a radius approximately 2.4 times larger than Earth, classifying it as a super-Earth. While uncertainties remain regarding its exact mass and composition due to current observational constraints, there is speculation that Kepler-22b could possess either a rocky surface or a global ocean covering its entirety. The concept of a world entirely covered by liquid water, devoid of exposed land, presents intriguing possibilities for supporting aquatic life forms. The star Kepler-22 plays a crucial role in assessing the potential habitability of its orbiting exoplanet, Kepler-22b. It belongs to the G-type category, akin to our Sun, but slightly smaller and cooler. G-type stars like Kepler-22 are considered favorable for life's development due to their stable and enduring energy output. This consistency contrasts with more volatile stars such as red dwarfs, which are prone to intense flaring. The stable stellar environment of Kepler-22 suggests that Kepler-22b may maintain a stable atmosphere, a critical factor for supporting life. However, the planet's ability to host life depends not only on its location within the habitable zone, but also on its atmospheric composition, which remains uncertain. An ideal scenario would involve an atmosphere capable of trapping heat through a greenhouse effect without leading to excessive warming or becoming inhospitable to life. Future observations, possibly through advanced telescopes like the James Webb Space Telescope, hold promise for unveiling the composition of Kepler-22b's atmosphere. These observations could reveal gases indicative of biological processes, providing key insights into the potential habitability of this distant world and advancing our understanding of planetary environments beyond our solar system. Discovered in 2009, WASP-17b stands out in the realm of exoplanets due to its extraordinary characteristics, earning it the nickname the Backwards Giant. Located roughly 1,000 light-years away in the constellation Scorpius, this gas giant boasts a radius nearly twice that of Jupiter, while only possessing half its mass. This results in an unusually low density, likening it to a celestial puffball in space. What truly distinguishes WASP-17b is its retrograde orbit, moving in the opposite direction to its host star's rotation, a rarity among exoplanets. This backward motion challenges conventional theories of planetary formation and migration. Typically, planets form from a rotating disk of gas and dust, aligning their orbits with their star's rotation. WASP-17b's retrograde orbit suggests a turbulent history involving gravitational interactions with other celestial bodies or nearby stars, potentially leading to significant alterations in its original orbit. These interactions could include gravitational slingshots from close encounters with other planets, or more gradual processes like Kozai cycles, which can transform a planet's orbital inclination over time, potentially flipping its orbit relative to its star. WASP-17b's atmospheric properties also intrigue scientists. Observations hint at the presence of water vapor and possibly carbon monoxide, yet its extended atmosphere and low density pose questions about its composition and weather dynamics. The intense radiation it receives due to its proximity to the host star could drive extreme atmospheric phenomena not seen in our own solar system. Located approximately 560 light-years away in the constellation Draco, Kepler-10b orbits its host star, Kepler-10, at an extraordinarily close distance, completing a full orbit in less than 20 hours. This close proximity exposes Kepler-10b to extreme temperatures, leading to its nickname, the roasting rocky world. The intense radiation from its host star heats Kepler-10b's surface to over 1,300 degrees Celsius, about 2,372 degrees Fahrenheit, hot enough to melt iron and rock, resulting in a landscape covered in molten lava. While these conditions make Kepler-10b inhospitable for life as we know it, they provide a unique opportunity to study the compositions and atmospheres of rocky exoplanets and the environments in which they form and evolve. Kepler-10b is predominantly composed of silicate rock, with a mass about 3.3 times that of Earth and a radius 1.47 times larger than our planets. These characteristics classify it as a terrestrial or rocky planet akin to Earth, Venus, Mars, and Mercury in our own solar system. However, its close orbit and resulting extreme temperatures underscore the diversity of planetary environments within our galaxy. The discovery of Kepler-10b was significant not only for confirming the existence of rocky exoplanets, but also for showcasing the capabilities of the Kepler telescope and the transit method of detecting exoplanets. By observing the slight dimming of a star's light as a planet passes in front of it, astronomers glean essential details about the planet's size, density, and orbital characteristics. For Kepler-10b, these observations have yielded crucial insights into rocky planets' properties, shedding light on their compositions and structures. Kepler-10b's close proximity to its host star raises intriguing questions about its formation and history. It likely formed farther out in its solar system and migrated inward over time, possibly through interactions with other planets or the protoplanetary disk from which it originated. Understanding these dynamic processes is vital for unraveling the complexities of planetary systems, including our own. Situated approximately 33 light-years away in the constellation Leo, Gliese 436b has captivated astronomers with its paradoxical nature since its discovery. Dubbed the burning ice planet, it challenges conventional ideas about planetary conditions and composition. Despite its close orbit around its host star, Gliese 436, completing a swift orbit in just over 2 days, the planet's surface is covered in a peculiar substance known as hot ice, a form of water existing under immense pressure and high temperatures. Gliese 436b boasts surface temperatures exceeding 400 degrees Celsius, 750 degrees Fahrenheit, conditions where water would typically exist as steam. However, the planet's intense gravitational forces compress water into an exotic variant called Ice X. Unlike normal ice, Ice X remains solid even at elevated temperatures due to the extreme pressure, creating a scenario where ice can endure in a near-stellar environment. This unique state of matter on Gliese 436b arises from its distinctive atmospheric and physical traits. The planet's hydrogen and helium-rich atmosphere, coupled with traces of water vapor, indicate the presence of water under extreme conditions. Instead of conventional forms, these conditions transform water into hot ice and supercritical fluid, a hybrid state blending liquid and gas properties. The discovery of Gliese 436b has profoundly enriched our comprehension of exoplanetary diversity and the array of survivable conditions. It challenges assumptions about water's behavior and the environmental prerequisites for various states of matter. The presence of hot ice on Gliese 436b hints at the potential existence of numerous planets with similarly unconventional environments, expanding our understanding of planetary diversity across the universe. Situated approximately 150 light-years away in the constellation Pegasus, HD 209458b, nicknamed Osiris, stands as a remarkable example among exoplanets due to its striking process of evaporation. This gas giant orbits its host star at a mere eighth of the distance between Earth and the Sun, resulting in surface temperatures surpassing 1,000 degrees Celsius, about 1,832 degrees Fahrenheit. Such close proximity subjects HD 209458b to intense stellar radiation, heating its atmosphere to the point where it expands and begins to escape into space. The phenomenon of atmospheric escape observed on HD 209458b was one of the earliest instances detected directly. Utilizing the Hubble Space Telescope, astronomers observed hydrogen, carbon, and oxygen being ejected from the planet at speeds reaching thousands of kilometers per hour, forming a vast, trailing tail of material akin to a comet. This escape process is so significant that it is estimated the planet loses between 100 million to 500 million kilograms of mass per second. The evaporation of HD 209458b offers crucial insights into the dynamic interactions between exoplanets and their host stars, especially in cases of planets in close orbits. The intense radiation driving atmospheric escape on Osiris also ionizes the escaping gases, which interact with the star's light, creating observable signatures that led to the discovery of this phenomenon. Space is a vast expanse filled with galaxies and planets, each holding mysteries that are both captivating and unsettling. When did humans first begin contemplating the possibility of extraterrestrial life? What are the origins and historical context of the Fermi paradox? How does the Drake equation estimate the potential number of technologically advanced civilizations in our Milky Way galaxy? In what manner does the Kardashev scale classify extraterrestrial civilizations? What is the Great Silence? Where are the signs from aliens? These are just a few of the mysteries we're unraveling in today's documentary. Let's go on a journey to explore these questions through a comprehensive scientific lens. When did humans first begin contemplating the possibility of extraterrestrial life? In ancient Greece and Rome, early thinkers like Democritus and Epicurus pondered the vastness of the cosmos and speculated about the existence of other worlds. They believed that the universe was made up of countless tiny atoms which randomly collided to form diverse worlds beyond our own. Epicurus's follower, Metrodorus, likened the idea of Earth being the only inhabited planet to expecting a single grain of wheat in an infinite field. Adding a poetic flourish to this philosophy, Roman poet Lucretius suggested that in the grand scheme of the universe, uniqueness was a rarity, implying the existence of numerous other Earth-like worlds bustling with life. While these ancient philosophers didn't conceive of stars as suns with planets like ours, they did imagine a universe teeming with diverse worlds. Their visionary ideas laid the groundwork for our modern fascination with extraterrestrial life, showcasing their forward-thinking perspectives on the cosmos. However, it's essential to note that their understanding differed from ours, as they viewed stars as fixed points on a celestial sphere rather than as distant suns with planetary systems like our own. In these times, thinkers envisioned other Earths as distant and isolated realms similar to today's concept of multiple universes, expansive, uncharted, and entirely separate from our own existence. However, as we transitioned into medieval times, the abstract musings of these early visionaries clashed with the more empirical views of Aristotelians who prioritized observable reality over imagination. Aristotle's immense influence led to the sidelining of the idea of many worlds. Nevertheless, this notion persisted, fueled by the tension between Aristotle's stance and the Church's belief in God's omnipotence. While the concept of many worlds remained dormant in philosophical discourse, it was ironically kept alive by the arguments used to discredit it, awaiting a resurgence. Medieval theologians emphasized that Aristotle's rejection of multiple worlds couldn't be treated as indisputable truth, leaving room for ongoing speculation within scholarly circles. In the 15th century, interest in extraterrestrial life was revived. Figures like Nicholas of Cusa proposed that life existed throughout the cosmos, extending beyond Earth. He posited that celestial beings created by God inhabited stars and planets of various ranks, offering a renewed perspective on the potential diversity of life beyond our world. Nicholas of Cusa proposed a fascinating idea. Beings inhabiting celestial bodies would likely differ from us, with those from sun-like planets potentially being more radiant and spiritual, contrasting with perhaps more diverse lunar beings, while earthly inhabitants might lean towards materiality. However, our understanding of these otherworldly beings remains limited, as we lack comparative standards. Unlike the Epicureans' notion of completely separate universes, Cusa envisioned a universe brimming with life, including various forms of beings on different celestial bodies, essentially what we now conceptualize as aliens. This concept sparked intense debate among medieval theologians, including Cusa's contemporaries, who grappled with profound questions. Did these beings experience a fall from grace akin to humans? Did they require redemption through Christ? French theologian William Vorilhon contributed to this discourse, suggesting that beings on other worlds were not burdened by Adam's original sin and thus lived free from its consequences. He proposed that Christ's sacrifice on earth held such profound power that it could extend across infinite worlds. However, he found it difficult to reconcile the idea of Christ suffering and dying multiple times on different worlds. Medieval scholars delved not only into the existence of inhabited worlds, but also into the theological implications, exploring how extraterrestrial life might intersect with Christian beliefs. They contemplated the cosmic role of humanity and the universal scope of Christ's salvation, weaving these concepts into the tapestry of their theological discourse. The prevailing notion that the Middle Ages were a dark era resistant to new ideas is challenged by evidence of medieval scholars engaging with the concept of extraterrestrial life. Surprisingly, this engagement didn't always lead to accusations of heresy or put lives at risk, hinting at a more complex intellectual environment than commonly assumed. During this period, curiosity about the universe and its potential inhabitants thrived, fostering debates and speculations about worlds beyond our own without immediate fear of condemnation. This challenges the stereotype of medieval scholars as closed-minded and stifling of innovation, revealing a more open and inquisitive scholarly culture. Nicholas of Cusa, for instance, was celebrated for his discussions on extraterrestrial life, earning him recognition as a cardinal and even a papal legate. Similarly, William Vorilhon who contributed to this discourse, faced no charges of heresy and was known for his opposition to the unjust trial of Joan of Arc, highlighting his commitment to justice and freedom of thought. These examples illustrate that the medieval period was intellectually diverse and less oppressive than commonly believed. In essence, ancient and medieval intellectuals were captivated by the idea of life beyond Earth. Early philosophers like the Greeks imagined separate worlds, while later medieval thinkers pondered the potential for other planets within our universe to host various forms of life. This intellectual journey represents a progression from abstract speculation to more concrete hypotheses about extraterrestrial existence, blending elements of philosophy, science, and theology. What are the origins and historical context of the Fermi paradox? Discussions surrounding the search for extraterrestrial life often center on two key concepts. The first is the Drake equation, a tool crafted by astronomer and SETI pioneer Frank Drake. This equation, backed by credible calculations, offers estimates reaching into the thousands of potential cosmic civilizations capable of emitting detectable signals. The second concept is the Fermi paradox, often misunderstood. It suggests that if intelligent aliens exist, their presence should be apparent through interstellar colonization. However, the absence of clear evidence on Earth raises doubts about the feasibility of detecting their signals. Interestingly, the Fermi paradox is incorrectly linked to physicist Enrico Fermi, who never actually proposed it. Despite its misattribution, this paradox has influenced debates on extraterrestrial intelligence and affected funding for related research. Senator William Proxmire, for instance, used it to argue for the discontinuation of NASA's SETI program in 1981. Though briefly revived due to advocacy from Carl Sagan, the program faced termination again in 1993 under Senator Richard Bryan. Despite the discovery of numerous exoplanets, federal funding for SETI initiatives in the United States has been lacking. Enrico Fermi himself, a Nobel laureate known for his contributions to nuclear physics, didn't leave behind any published works on extraterrestrial life. Our understanding of his views on the matter stems from accounts gathered by physicist Eric Jones from individuals present at a 1950 Los Alamos luncheon, Emil Konopinski, Edward Teller, and Herbert York, who outlived Fermi. The concept often referred to as the Fermi paradox traces back to an event where Herbert York and Edward Teller interpreted physicist Enrico Fermi's remarks as questioning the feasibility of interstellar travel rather than doubting the existence of extraterrestrial life. Thus, the term Fermi paradox, which implies skepticism about aliens, doesn't accurately reflect Fermi's stance. His skepticism about space travel aligned with the technological limitations of his time. Rocket technology in 1950 hadn't achieved orbital launch, let alone interstellar travel. The idea that the absence of extraterrestrials on Earth implies their non-existence wasn't initially proposed by Fermi, but by astronomer Michael Hart in 1975. Hart argued that intelligent aliens would inevitably colonize the Milky Way, and their absence here suggests humanity might be alone in the galaxy. This viewpoint, though criticized, has influenced discussions on extraterrestrial life. Physicist Frank Tipler expanded on Hart's thesis in 1980, addressing the resource requirements for galactic colonization. He proposed a self-replicating universal constructor capable of populating the entire galaxy. Tipler concluded that Earth's lack of such advanced technology implies humanity's uniqueness not only in the Milky Way, but in the entire universe. However, drawing such significant conclusions from the absence of encounters with extraterrestrial beings on Earth has faced challenges. Critiques include the possibility of unattainable interstellar travel, civilizations choosing not to colonize, or past alien visitations leaving no discernible traces. Despite these counter-arguments, Hart's and Tipler's hypotheses have left a mark on the discourse surrounding extraterrestrial life. The fundamental idea commonly known as the Fermi paradox is actually the result of the work of Hart and Tipler. Over time, their concept has become mistakenly associated with Fermi's initial inquiry. This confusion can be traced back to physicist David G. Stevenson, who in 1977 labeled it the Fermi paradox in a publication, suggesting Hart's theory as an answer to Fermi's question. A more precise term for this line of thought would be the Hart-Tipler argument against the existence of technological extraterrestrials. While this label might not carry the same historical weight as its misattributed counterpart, it would be a more accurate acknowledgement of its true originators. How does the Drake equation estimate the potential number of technologically advanced civilizations in our Milky Way galaxy? The core of this thought-provoking inquiry lies in the comparison between two profound possibilities: the existence of numerous extraterrestrial civilizations throughout our galaxy, or the solitary nature of humanity in the vastness of space. Consider the scale of the universe. It's teeming with an incomprehensible number of stars. Even within our own Milky Way, estimates range from 100 billion to 400 billion stars. And this is just one galaxy among countless others scattered across the cosmic expanse. Given this immense scale, the sheer quantity of stars suggests the tantalizing possibility that we are not alone, despite the potentially minuscule odds of intelligent life emerging. Frank Drake, a pioneering figure in this quest for understanding, sought to tackle this cosmic puzzle. He outlined a series of questions that scientists must address to estimate the number of detectable civilizations within our galaxy. By combining these questions through multiplication, Drake devised the now famous Drake equation, providing a framework for estimating the potential abundance of detectable civilizations. Within the intricate framework of the Drake equation, each symbol holds a key to understanding our cosmic potential. R* symbolizes the ongoing creation of stars in our galaxy, a celestial symphony unfolding annually. Moving forward, FP represents the fraction of these stars hosting planetary systems, setting the stage for the next question: which of these planets reside within the habitable zone? This crucial aspect of our cosmic puzzle is quantified by Ni, a value shrouded in the mysteries of extrasolar planets. While these worlds may offer potential habitats for life, the true extent of their habitability remains uncertain, a question addressed by FL in the enigmatic Drake equation. Phi sheds light on the number of habitable planets where intelligence has emerged. Frank Drake's gaze turned toward the realm of radio astronomy, envisioning his equation as a tool to gauge the likelihood of extraterrestrial civilizations communicating through detectable signals, an idea encapsulated by FC. In the 1960s, radio was widely seen as the preferred means of communication for advanced civilizations. Earth itself has been broadcasting a technological signal into space for nearly a century, potentially reaching out to neighboring stars within an 80 light-year radius, each one a potential listener to the whispers of life. However, a lingering question persists. Would advanced civilizations across the cosmos still communicate via radio waves, or might they consider such a method as outdated as smoke signals are to us? There's a possibility that some alien societies might intentionally conceal their presence from potential cosmic peers. In a diverse cosmos, it's conceivable that not all civilizations hold benevolent intentions, making the disclosure of one's cosmic whereabouts a risky proposition. The final variable in the Drake equation carries a weighty implication. It seeks to gauge the duration for which a technological civilization remains detectable. Represented by L. Frank Drake, harbored concerns that a highly advanced society might shine brightly, yet fleetingly, on the cosmic stage of observability. It's plausible that many civilizations, though they may endure for eons, could only be within our reach for a fleeting moment in their extensive histories. So what's the solution? When Drake initially formulated his estimates in 1961, he concluded that N, the number of detectable civilizations in our galaxy, likely ranged between 4 and 10. However, refining Drake's parameters with modern scientific insights paints a different picture. The revised calculation for N is a mere 0.00127, indicating that within any given 100,000-year period of our galaxy's existence, approximately 127 civilizations could emerge within the realm of detection. The foundation of Drake's work rested on the belief that extraterrestrial civilizations populate our galaxy. His calculations hinted at a rich tapestry of around 10,000 civilizations within the Milky Way alone. Despite the enormity of this figure, the sheer magnitude of the challenge in detecting even a single civilization among the galaxy's minimum of 100 billion stars underscores the immense task confronting astronomers. It suggests that a meticulous examination of 10 million stars is imperative before any skepticism regarding their prevalence can be warranted. In what manner does the Kardashev scale classify extraterrestrial civilizations? The observable universe, spanning over 13 billion years, presents a staggering expanse, housing approximately 2 trillion galaxies, each adorned with an estimated 20,000 billion stars. Within our Milky Way alone, scientists speculate the presence of around 40 billion Earth-like planets nestled within their stars' habitable zones. Such astronomical figures suggest that Earth may not be the sole cradle of life in the universe. The revelation of life elsewhere would revolutionize our cosmic outlook, revealing a vibrant cosmos teeming with existence. This realization could potentially elevate our collective consciousness, fostering unity in place of terrestrial discord. Yet, before embarking on the cosmic quest for potential interstellar companions or adversaries, we confront a fundamental quandary, defining the precise nature of what we seek in the universe's vast expanse. In a universe as expansive and ancient as ours, it's reasonable to assume that civilizations emerge over intervals spanning millions of years, evolving along diverse paths and at varying rates. This implies that our search encompasses not only vast distances reaching hundreds of thousands of light years, but also civilizations ranging from primitive to highly advanced. To refine our search for extraterrestrial life, we require a conceptual framework that aids us in thinking more effectively. Since humanity serves as our sole reference point, we must exercise caution when drawing conclusions based solely on our own experiences. However, certain insights can still be gleaned from our history. Humans, propelled by competition, the pursuit of resources, and a natural inclination for expansion, began their journey with basic tools and innate curiosity. These traits have played pivotal roles in the development of our civilization, driving significant advancements. It stands to reason then that extraterrestrial beings capable of dominating their own planets might exhibit similar characteristics. Furthermore, if these alien species are governed by the same physical laws as us, their technological progress could potentially be measured by their energy consumption. This perspective offers a potential metric for evaluating the advancement of extraterrestrial civilizations. Human progress, for instance, can be traced through our evolving ability to harness energy from our environment. Our journey commenced with the utilization of muscle power, evolved to mastery of fire, and further expanded to harnessing kinetic energy from natural sources like water and wind through mechanical means. With advancements in technology and material science, we progressed to tapping into the dense energy of fossil fuels. This escalation in energy utilization has paralleled our civilizational advancements. Expanding upon these insights, scientist Nikolai Kardashev introduced a system to classify civilizations based on their energy consumption, the Kardashev scale. This scale, although refined over time, primarily categorizes civilizations into 4 distinct levels. A Type 1 civilization harnesses the energy of its home planet, while a Type 2 civilization extends its reach to harness the energy of its star and planetary system. Advancing further, a Type 3 civilization exploits the energy resources of its entire galaxy, and a Type 4 civilization transcends its energy usage to encompass multiple galaxies. Each level on this scale represents a significant leap in complexity and capability, akin to the difference between an ant colony and a human city. To an ant, the structures and systems of a human city would appear godlike in their sophistication. To make the Kardashev scale more practical, it's beneficial to incorporate subcategories for a more nuanced understanding of the vast disparities in civilization development. Within the Kardashev scale, civilizations ranging from Type 0 to Type 1 span a spectrum from primitive societies to those comparable to what we might achieve in a few centuries. Such civilizations could potentially be abundant within the Milky Way. However, the absence of active radio signal transmissions into space means that even civilizations in close proximity, such as those in the Alpha Centauri system, could remain undetected. Our own radio broadcasts, covering a radius of 200 light-years, are minuscule compared to the vastness of the Milky Way and degrade into indistinguishable noise after traveling just a few light-years. At present, humanity finds itself at approximately level 0.75 on the Kardashev scale. We've made significant alterations to our planet, constructing massive infrastructure, reshaping landscapes, and modifying the atmosphere's composition and temperature. If we manage to preserve Earth's habitability, there's potential for us to advance to a full Type 1 status within the next few centuries. Achieving this status signifies a natural progression toward venturing beyond Earth, driven by our inherent curiosity, competitive spirit, and expansionist tendencies. The transition to becoming a Type 2 civilization entails extensive forays into space. This journey might commence with the establishment of space outposts, evolving into the development of space-based infrastructure and industries, leading ultimately to the colonization and terraforming of other planets. As a civilization's activities and resource utilization expand, so too do its energy requirements. A pivotal milestone for an emerging Type 2 civilization would be the construction of a Dyson swarm encircling their star, providing nearly limitless energy for vast system-wide projects. With such capabilities, the aspirations of a Type 2 civilization would naturally extend to other star systems, reminiscent of our current perception of the distance to Pluto, challenging yet within reach with substantial effort and resources. This heralds the commencement of their journey toward becoming a Type 3 civilization. The challenges inherent at this stage are beyond our current comprehension, including traversing vast distances and maintaining coherence across light-years, both culturally and biologically. It prompts questions about whether such a civilization could surmount the immense travel times, retain a unified identity across distant colonies, or if they might diverge into distinct civilizations or even separate species. The journey toward becoming a Type 3 civilization involves navigating not only physical distances, but also potential existential risks lurking in the interstellar void, as a civilization progresses toward Type 3. Status on the Kardashev scale, envisioning their form and nature becomes increasingly daunting. These civilizations might uncover novel principles of physics, master dark matter and energy, or even achieve faster-than-light travel. Their motives, technology, and actions could surpass human comprehension. In this context, we humans are akin to ants attempting to decipher the complexities of a galactic metropolis. To a highly advanced Type 2 civilization, humanity might appear too primitive for meaningful interaction, while a Type 3 civilization might regard us as we view bacteria on an anthill, possibly disregarding our consciousness or survival as inconsequential. In such a scenario, we can only hope for benevolence from these entities. However, the scale of civilization might extend even further. Some theorists speculate about the existence of Type 4 and Type 5 civilizations, wielding influence over galaxy clusters or superclusters spanning thousands of galaxies and trillions of stars. At the apex of this scale lies the hypothetical Type Omega civilization, capable of manipulating the entire universe and conceivably creating new universes. While speculative, this classification offers intriguing insights. If our assumptions about interstellar civilizations hold some truth, then the likelihood of Type 3 or higher civilizations existing near the Milky Way is exceedingly low. Their presence would be unmistakable, with clear signs of their activity spanning numerous star systems. Yet the absence of such evidence, such as harvested stars, decaying megastructures, or remnants of interstellar conflicts, suggests they do not exist nearby. This realization, although somewhat disheartening, also offers reassurance by suggesting that the galaxy remains open for humanity and civilizations akin to ours. The most probable extraterrestrial civilizations to discover would likely fall within the range of Type 1.5 to Type 2.5, advanced enough to be captivating yet not so advanced as to be beyond comprehension. These civilizations might be involved in constructing megastructures, voyaging between stars, and potentially transmitting vast amounts of information into space. However, it's conceivable that our comprehension of progress toward Type 2. Civilization is limited, and humanity's inclination toward outward expansion might reflect our current developmental stage. At present, our quest for extraterrestrial life is still in its early stages. Until we encounter advanced alien civilizations capable of unraveling the mysteries of the universe, we are left to our own devices in exploring the secrets of the cosmos. What is the Great Silence? Where are the signs from aliens? The haunting silence that greets our search for extraterrestrial life in a universe teeming with countless stars and planets is a perplexing phenomenon known as the Great Silence. It suggests a vast cosmos devoid of detectable signals or signs from alien civilizations, challenging our comprehension of the seemingly boundless expanse of space. In 1967, Jocelyn Bell, a postgraduate student at Cambridge University, was conducting sky surveys using a novel radio telescope when she stumbled upon a peculiar radio signal pulsing regularly every 1.33 seconds. Initially dismissed as human-made interference, further investigation revealed that the signal originated from deep space. Its consistent timing defied previous observations, sparking speculations about extraterrestrial origins. Humorously dubbed LGM-1, an acronym for Little Green Men, reflecting the initial excitement surrounding the possibility of alien communication, the mystery was soon dispelled as a natural phenomenon. The signal emanated from a pulsar, a rapidly spinning neutron star emitting radiation beams akin to the light beams of a lighthouse. Although this discovery debunked the alien theory, it catalyzed a global initiative known as the Search for Extraterrestrial Intelligence, SETI, aimed at detecting artificial transmissions from space. Despite extensive efforts, humanity has yet to discover definitive extraterrestrial signals. For about a century, we've unintentionally been sending radio signals into space, creating a radio bubble extending roughly 100 light-years from Earth. Within this range, extraterrestrial civilizations might be alerted to our presence. However, beyond this bubble, Earth's existence is virtually undetectable. Moreover, as technology advances, our unintentional radio emissions are diminishing, potentially leading to a future of radio silence. The fleeting lifespan of a civilization's radio signals in the cosmic timeline presents a challenge for interstellar communication. Additionally, these signals weaken as they traverse space. Military radar signals, being among the strongest leaks into space, have a higher chance of detection over vast distances compared to standard TV broadcasts. The upcoming Square Kilometre Array, a large interferometer in South Africa and Australia, may detect faint signals from Earth-like civilizations up to several hundred light-years away. Deliberate communication attempts, like the 1974 Arecibo message sent from Puerto Rico toward a distant star cluster, offer a more focused approach. However, these efforts are transitory, providing extraterrestrial observers with a limited window for detection. An example of a potential extraterrestrial signal is the 1977 WOW signal, a brief burst of energy that remains unexplained and hasn't been detected again. Ultimately, the chance of two civilizations coincidentally discovering each other by randomly broadcasting is slim. To enhance our prospects of contact, we need to refine our search strategies, concentrating on signs of technological and biological life in the cosmos. In 1995, astronomers achieved a groundbreaking milestone, the discovery of the first planet orbiting a star similar to our Sun outside our solar system. Subsequently, we've learned that most stars in our galaxy likely host at least one planet, with billions resembling Earth in size and orbiting within their star's habitable zone. This zone offers the potential for liquid water, a crucial ingredient for life as we understand it. Even moons orbiting these extrasolar planets might harbor life, with estimates suggesting there could be as many as 1 billion moons like this. Recognizing the potential for extraterrestrial life, in 2017, a deliberate message was sent to one of the most Earth-like exoplanets we've discovered, relatively close to us. This message contained musical compositions and information about humanity. If the planet is inhabited and capable of responding, we could potentially receive a reply by 2044. However, confirming whether a planet actually hosts life requires meticulous examinations, such as analyzing the chemical composition of its atmosphere. This is achieved by studying the starlight that passes through it. For instance, an atmosphere rich in oxygen, akin to Earth's, might imply the presence of life, as oxygen on our planet is largely generated by photosynthetic organisms. Nevertheless, the mere presence of oxygen isn't definitive evidence, as it can also arise from non-biological processes. Astrobiologists are particularly intrigued by specific combinations of chemicals that are unlikely to coexist without life, such as methane and carbon dioxide. Additionally, chemicals like carbon dioxide could indicate industrial activities and climate alterations, serving as potential indicators of intelligent life. Beyond these biosignatures, we may also detect technology-related cues known as technosignatures. For instance, an exoplanet adorned with a dense array of artificial satellites or space debris might be discernible when it passes in front of its star. Theoretical concepts like Dyson spheres, envisioned by physicist Freeman Dyson, represent another avenue of exploration. These speculative megastructures would be constructed by advanced civilizations to harness a star's energy. The Kardashev scale, proposed by astrophysicist Nikolai Kardashev, categorizes civilizations based on their energy usage. A Type 1 civilization utilizes its planet's energy, Type 2, its star's energy, and Type 3, the energy of an entire galaxy. While there's no confirmed evidence of Type 2 or 3 civilizations in the Milky Way, these concepts propel our quest for extraterrestrial intelligence. Occasionally, intriguing astronomical events ignite speculations about aliens. Take, for example, a distant star with erratic dimming patterns, which initially prompted theories about colossal alien structures obstructing its light. However, subsequent investigations suggest this phenomenon is likely due to dust, not extraterrestrial engineering. Despite such speculative musings, the pursuit of concrete evidence of extraterrestrial life persists. Particularly, astronomers remain fascinated by the hunt for life beyond our galaxy. Despite exhaustive surveys spanning 100,000 galaxies in search of signs of a Type 3 civilization capable of harnessing the energy of an entire galaxy, no traces of such an advanced society have surfaced. This profound cosmic silence raises significant questions, especially considering Earth's prolonged emission of detectable biosignatures for roughly 1 billion years, seemingly without attracting any discernible attention from alien beings. This disparity between the high likelihood of extraterrestrial life and the dearth of tangible evidence prompts what's known as the Fermi paradox. One plausible explanation is that life, especially intelligent life, is exceedingly rare. Earth's evolutionary journey, punctuated by numerous mass extinctions before the emergence of humans, lends credence to the rare Earth hypothesis. This hypothesis suggests that the development of complex life on our planet stemmed from a sequence of improbable events, potentially making Earth's life story a unique occurrence in the vastness of the universe. Speculations about the existence of a great filter, a formidable obstacle to life's evolution, abound. If this filter lies in the past, Earth may have successfully navigated it, rendering us among the fortunate few. Conversely, if it lies ahead, humanity could confront an existential threat that spells its demise. Another realm of conjecture centers on the nature of alien life. While life on Earth is carbon-based and thrives in water, extraterrestrial life might manifest in radically different forms, like silicon-based organisms dwelling in ammonia oceans. Such diversity could lead us to overlook signs of alien life because we're fixated on familiar terrestrial models. Moreover, there's the intriguing notion that advanced civilizations might transcend physical reality altogether. The transcension hypothesis, advanced by futurist John Smart, posits that such civilizations might retreat inward, engrossed in crafting hyper-realistic simulations and exploring virtual realms instead of the physical cosmos. Eventually, their technology could shrink to a scale akin to black holes, effectively rendering them invisible in the observable universe. In our quest for extraterrestrial intelligence, artificial transmissions and signs of astroengineering remain pivotal. Take, for instance, the iconic Voyager 1 and Voyager 2 missions launched in 1977, representing humanity's fervent outreach to potential extraterrestrial civilizations. These spacecraft, each bearing a golden record brimming with information about our species and the diversity of life on Earth, serve not only as cosmic explorers, but also as envoys, tasked with delivering messages to any extraterrestrial beings they may encounter, Voyager 1 embarks on a journey spanning 40,000 years, destined to traverse the interstellar void and approach another star system, while Voyager 2, taking a divergent route, has provided invaluable insights into the outer reaches of our solar system and ventured into interstellar space in 2018. As these probes traverse the cosmic expanse, they symbolize humanity's insatiable curiosity and our relentless quest to comprehend our cosmic abode, while their transmissions back to Earth enrich our understanding of the universe. Yet this technological prowess begets a confounding question. Why does our solar system seem devoid of such emissaries? Given the rapid pace of human technological advancement, one might expect the galaxy to be bustling with self-replicating automatons. Yet no tangible evidence supports this notion. Searches for alien artifacts within our solar system have yielded no confirmed discoveries, but the sheer vastness of space means that extraterrestrial objects could effortlessly evade detection. In 2017, an enigmatic visitor from beyond our solar borders, dubbed Oumuamua, stealthily traversed the inner reaches of our celestial neighborhood, eluding detection until its outbound trajectory from the Sun. Its serendipitous detection hinted at the possibility of numerous similar objects slipping past our surveillance. Oumuamua's peculiar morphology and anomalous behavior, initially categorized as a comet, then re-evaluated due to its absence of a cometary coma and unexpected acceleration, ignited debates regarding its nature, including conjectures of it being an interstellar probe potentially propelled by a light sail. However, Oumuamua remained obstinately radio silent, akin to a derelict probe aimlessly wandering the cosmos, akin to Voyager. Our comprehension of life beyond Earth is circumscribed by our solitary example, our planet. The discovery of life elsewhere, even within our solar confines, such as beneath the icy crust of Europa, would furnish invaluable insights into the prevalence of life throughout the cosmos. The endeavor to unravel the mystery of the Great Silence has witnessed remarkable strides in recent years. The deployment of the James Webb Space Telescope in 2021 revolutionized the scrutiny of exoplanetary atmospheres, augmenting our capacity to detect potential signs of life. Initiatives like Breakthrough Listen have galvanized the search for extraterrestrial intelligence, employing more refined detection methodologies. The heightened scrutiny of Oumuamua-like interstellar interlopers has catalyzed discussions concerning their origins, whether artificial or if it was natural. The 2021 landing of the Perseverance rover on Mars marked a pivotal stride in the quest for biosignatures, deepening our comprehension of the potential for life within our solar neighborhood. Concurrently, astrobiology is delving into the viability of life in extreme environments, expanding the vistas of our pursuit of extraterrestrial life forms. These endeavors underscore an escalating dedication to unraveling the enigmas of the cosmos, recognizing the discovery of extraterrestrial life as an epochal milestone in human annals. Numerous scientists contest the notion of Earth as an unparalleled cosmic phenomenon, citing the abundance of Earth-like planets and life's resilience on our planet. Yet, the precise likelihood of life, particularly intelligent life, remains shrouded in uncertainty. The conditions requisite for abiogenesis, the transition from non-life to life, elude complete comprehension. Deeming ourselves solitary inhabitants of the universe lacks substantiation without further evidence. Our exploration for extraterrestrial intelligence remains circumscribed, akin to scouring for fish in a glass of water when juxtaposed with the vastness of the oceans. Space unfurls in boundless expanses, and our expedition has barely commenced. Multifarious, unexplored avenues for detecting life await our scrutiny. By fine-tuning our telescopic apparatus, expanding their dimensions and tuning into divergent frequencies, we may unveil that the universe resonates with vitality far beyond our present discernment. What is the Great Filter hypothesis? Do we stand a chance at surviving? Space exploration stands as one of humanity's most extraordinary triumphs, with a plethora of exhilarating discoveries looming on the horizon. Yet, amidst this progress, a haunting query looms. Could our advancement be abruptly halted by an existential menace? The cosmos may eventually unveil a stark verity to humanity, the inescapable denouement that awaits all life forms. Enter the Great Filter theory, a speculative framework positing that every sentient civilization will confront seemingly insurmountable hurdles at some juncture, culminating in their inexorable decline, sans leaving enduring vestiges of their existence. Economist Robin Hanson introduced this hypothesis in 1996 as a plausible explanation for the Fermi paradox, the seeming incongruity between the high likelihood of extraterrestrial life and the paucity of substantiating evidence or interactions with such civilizations. Hansen postulated that the emergence of sentient life could be exceedingly rare, perhaps owing to enigmatic scientific constraints inhibiting life forms from evolving into sophisticated societies capable of cosmic exploration. If this conjecture bears veracity, it intimates that humanity might confront analogous insuperable obstacles, potentially precipitating our own eventual demise. The Great Filter concept proffers hypothetical impediments to the progression of sentient life. These barriers might have manifested in the past, stymieing the ascent of organisms to sapience, or they could lurk in the future, presenting an existential threat to any advanced society. This theory intimates that the smoother the evolutionary trajectory hitherto, the more formidable the forthcoming challenges confronting humanity may prove to be. At its core, if humanity has yet to confront its Great Filter, it stands to reason that such a hurdle lies ahead. Initially met with skepticism, this hypothesis challenges conventional wisdom. The smooth evolutionary trajectory witnessed on Earth implies that analogous conditions could exist elsewhere, potentially fostering the emergence of other sapient life forms. This notion finds support in the Drake equation, which estimates the presence of several dozen advanced civilizations within the Milky Way. These civilizations might have pioneered technologies akin to our own in radio astronomy or spacecraft, rendering the prospect of interstellar interaction tantalizingly feasible. Yet, despite our diligent endeavors to detect extraterrestrial intelligence, the cosmos remains reticent. This conspicuous absence of evidence finds a plausible explanation in the Great Filter, positing that this unseen obstacle may account for our failure to discern any traces of other advanced life forms in the vast cosmic expanse. The Great Filter hypothesis postulates that advanced civilizations must navigate one or more pivotal challenges throughout their evolutionary journey. The existence of such filters offers a plausible rationale for the conspicuous silence pervading our search for cosmic companions. This framework allows for the possibility that certain species may surmount the Great Filter by traversing several crucial phases. Initially, the presence of a habitable planet within its star's Goldilocks zone is imperative. Life must then emerge and evolve, leveraging complex molecules like DNA and RNA for reproduction. The transition from single-celled to complex multicellular organisms represents a pivotal juncture, as does the advent of sexual reproduction, fostering genetic diversity. These evolutionary milestones should culminate in the emergence of sophisticated organisms proficient in tool usage and technological advancement, ultimately attaining a level of sophistication conducive to space colonization. The ultimate objective is the colonization of distant planets and star systems to avert self-annihilation. Robin Hanson contends that only upon achieving space colonization can a civilization truly regard the Great Filter as a trial of the past. Presently, humanity finds itself at a crucial juncture in its evolutionary journey, confronted with the formidable imperative of extending its reach beyond Earth to ensure survival. Hanson posits that an intelligent species invariably encounters a pivotal, potentially existential barrier within one of 9 evolutionary phases. This hurdle, if insurmountable, could spell the species' demise. While humanity may have surmounted 8 of these stages, the prospect of navigating the 9th, synonymous with space colonization, remains shrouded in uncertainty and may constitute the ultimate trial that could precipitate our extinction. The Great Filter hypothesis delineates various factors that civilizations must confront to avert self-obliteration, encompassing the prevention of internal conflicts, the mitigation of irreversible environmental degradation, and the sustainable management of natural resources. This theoretical construct not only informs our conceptual understanding, but also holds practical implications for shaping our strategies in space exploration. According to this paradigm, the discovery of extinct multicellular life on celestial bodies like Mars would be disconcerting, hinting that the evolutionary stages traversed thus far might have constituted the relatively manageable obstacles, with more formidable challenges looming ahead. The simplicity of the evolutionary trajectory on other planets inversely correlates with humanity's likelihood of evolving into a spacefaring civilization. Nonetheless, the scenario isn't entirely bleak. It remains plausible that humanity has already surmounted the most formidable hurdle on its evolutionary odyssey. Consequently, some scholars contend that our apparent cosmic solitude might paradoxically signify a positive omen, suggesting that we've adeptly navigated through the treacherous shoals of the Great Filter. Nevertheless, it's imperative to acknowledge that our current modes of communication represent only a fraction of the potential methods that might exist. Across the universe's vast expanse, spanning an estimated 13.8 billion years, myriad organisms may have confronted analogous obstacles. However, their lack of awareness of one another persists, often due to the necessity of monumental technological advancements, an irony underscored by humanity's own trajectory. On Earth, our march of progress has perilously propelled us towards the precipice of potential self-obliteration, epitomized by the specter of nuclear conflict. The looming specter of our civilization's potential annihilation before the fruition of more sophisticated propulsion or communication technologies looms large. Pinpointing the elusive Great Filter proves to be a formidable task, compounded by the staggering diversity of planetary conditions across the cosmos. Abiogenesis, the intricate transition from inorganic to organic matter, emerges as a plausible candidate for the Great Filter, potentially stymieing the evolution of numerous intelligent species. In light of the Great Filter hypothesis, profound uncertainties shroud humanity's trajectory. Are we equipped to surmount an unforeseen challenge with resolute efficacy? Or have we already triumphed over the most formidable phase? Might the universe's profound silence signal that we rank among the scant species to have successfully navigated the myriad hurdles posed by the Great Filter? Alas, these inquiries persistently elude definitive answers. At present, our recourse lies solely in fortifying ourselves for the unforeseeable trials or tribulations that the cosmos may yet lay at our feet. Rare Earth hypothesis. Is complex life rare in the universe? It's truly remarkable to contemplate our existence in one of the universe's rare oases where life can thrive, where the inhospitable extremes of suffocation, freezing, burning, or dehydration don't swiftly extinguish life's flame. It's as though we've stumbled upon an extraordinary stroke of luck. Nestled comfortably within Earth's biosphere, our unique position affords us a privileged vantage point from which to behold the cosmos. This perspective offers intriguing insights into the Fermi paradox. It seems logical that we would inhabit a planet hospitable to life in a universe capable of birthing such life-sustaining worlds. The anthropic principle proposes that our presence here is no coincidence. Rather, it reflects an inherent bias toward observation. The strong anthropic principle takes this a step further, suggesting that any universe we observe must inherently possess the conditions requisite for the emergence of observers like us. We'll delve into the ramifications of this notion, which includes the contentious notion of multiple universes. However, for now, our focus rests on the weak anthropic principle, a concept of profound significance despite its seemingly modest label. It posits that our existence necessitates placement within a universe conducive to our survival, such as a planetary biosphere, rather than amidst the barren void between galaxies. Though this assertion may appear self-evident, acknowledging this observer-centric bias proves pivotal in comprehending why the universe presents itself to us as it does. When we consider the weak anthropic principle alongside the conspicuous absence of extraterrestrial civilizations, it could imply that intelligent life is extraordinarily rare in our cosmos. To grasp this, ponder the essence of being an intelligent observer. The very act of contemplating these questions constitutes a singular mental experience, an experience you're currently undergoing. The kind of consciousness you possess, your very existence, might indeed be exceedingly rare, perhaps even singular, existing only within highly specific environments. Yet here you are, experiencing this consciousness, embodying it fully. Regardless of the rarity of such life-supporting environments, you inevitably find yourself within one of them. The weak anthropic principle does not prescribe the scarcity of these environments. Consider this. If there exists only one planet teeming with life in the entire galaxy, or even across the entire universe, it's the one you would inhabit. This notion leads us to the rare Earth hypothesis, which posits that a confluence of unique factors renders Earth an exceptionally rare and ideally suited planet for nurturing intelligent life. This hypothesis finds support not just in the extraordinary characteristics of our planet, which we'll delve into shortly, but also in the conspicuous absence of extraterrestrial life. The Fermi paradox underscores the jarring contradiction between the countless potential havens for life in the galaxy and the stark dearth of evidence for other galactic civilizations. We've previously explored the Fermi paradox and its various conjectures, but let's entertain the notion that the paradox holds true as it seems. Technological civilizations are exceedingly rare, possibly because planets like Earth are exceptionally scarce. Discussions surrounding the Fermi paradox often gravitate toward the concept of the Great Filter, a series of arduous or improbable steps in the evolution from a barren planet to a technologically advanced civilization. One such filter could be an impending peril, such as climate catastrophe or nuclear holocaust, which still poses a threat to our existence. However, the rare Earth hypothesis offers a somewhat more hopeful perspective, suggesting that planets capable of nurturing civilizations akin to ours are extraordinarily rare. This idea gained prominence through the work of Peter Ward and Robert Brownlee in their 2000 book, which meticulously examines the unique attributes of Earth necessary for the emergence of life and intelligence. Before we delve into Earth's distinctive qualities, it's crucial to acknowledge what's not rare about Earth. Planets resembling Earth are actually quite common. These rocky planets, akin in size to Earth, orbit stars resembling our Sun at a distance conducive to liquid water, what scientists dub the habitable or Goldilocks zone. The Kepler mission hinted at the possibility of around 10 billion such planets in our galaxy, a number that could soar to 40 billion if we include planets orbiting other types of stars. With billions of potential nurseries for life within the Milky Way, the notion persists that if even one civilization had a slight head start over us, it could have conceivably colonized the entire galaxy by now. This notion beckons the consideration that Earth might harbor unique attributes, rendering true Earth-like planets far scarcer than we imagine. Assessing Earth's singular characteristics vital for sustaining life allows us to gauge their rarity. Should any other planet share a life-critical trait with Earth, that trait might be relatively prevalent. However, if a feature is exclusive to Earth, it could be exceedingly rare. According to the weak anthropic principle, it's hardly surprising that we find ourselves on one of the scant planets endowed with these distinctive qualities. Presently, our understanding of exoplanets remains circumscribed, so let's juxtapose Earth with the other rocky denizens of our solar system. Two conspicuous qualities distinguish Earth. One, its dynamic interior, and two, its substantial moon. At the Earth's core lies a solid iron inner core encased within a molten metal outer core. The churning within this core engenders a robust magnetic field, shielding Earth from pernicious cosmic radiation and solar tempests. Beyond the core lies the solid yet malleable mantle-propelling plate tectonics. The Earth's lithosphere is partitioned into plates that drift and intermittently plunge back into the mantle, a phenomenon known as subduction. This tectonic dynamism not only precipitates alterations in ecosystems, but also fosters biodiversity by instigating environmental transitions. The recycling of nutrients from the Earth's crust into the mantle and subsequently into the atmosphere via volcanic eruptions is indispensable for upholding a fecund biosphere. In stark contrast, Mars exhibits minimal tectonic activity, while Venus, if any, is negligible, with neither planet boasting a shielding geomagnetic shield. While the frequency of tectonic activity on exoplanets remains uncertain, it's conceivable that such activity is a rarity. Earth's moon looms large in comparison to the satellites of other rocky planets in our solar system, a characteristic that might be exceedingly rare on a cosmic scale. Its dimensions, composition, and orbital path suggest it likely coalesced from the debris of a cataclysmic collision between a Mars-sized protoplanet and the nascent Earth. This cosmic crash could have wielded profound influence on the development of life on Earth, potentially shaping several pivotal facets. The impact is believed to have hastened Earth's rotation, yielding shorter nights crucial for photosynthesis and establishing Earth's axial tilt. A moderate tilt is posited to be vital for life, fostering seasons of manageable temperance. Earth's tilt appears to inhabit a Goldilocks zone, a potential rarity in the cosmos. Furthermore, the collision might have jump-started Earth's tectonic activity by fracturing its early crust. Moreover, the Moon's gravitational tugs could have intensified ongoing tectonic motions. An alternative theory proposes that the Moon played a role in abiogenesis. This hypothesis conjectures that life emerged in tidal pools, where the Moon's gravitational pull fostered conditions conducive to the genesis of intricate chemicals and protocells. Moreover, our solar system as a whole exhibits remarkable singularity. The revelations from the Kepler mission concerning other planetary systems underscore this distinctiveness. Our solar system boasts a diverse array of planet types, spanning from diminutive rocky worlds like Mercury to colossal gas giants like Jupiter and Saturn. This spectrum of celestial bodies diverges from the norm observed in other systems, where planets tend to exhibit more uniformity in size. Grandiose planets akin to Jupiter and Saturn are a rarity, constituting merely about 10% of systems. Jupiter, in particular, may have played a pivotal role in nurturing life's emergence by assuming the mantle of a cosmic guardian. Its formidable gravitational influence likely ensnared myriad comets and asteroids that might otherwise have collided with Earth, thereby averting numerous mass extinction cataclysms and potentially facilitating the unhindered march of life and evolution. Various other factors may contribute to Earth's exceptionalism, encompassing an especially conducive atmosphere, abundant water reservoirs, and the fortuitous evasion of cosmic perils such as gamma-ray bursts. However, what might truly set Earth apart within the cosmic tapestry is the singular trajectory of its evolutionary saga. Life, particularly in its nascent forms, could be widespread, but the transition from rudimentary organisms to complex life forms, or the blossoming of intelligence, might entail exceedingly rare evolutionary leaps. A notable instance of such rarity is the genesis of the eukaryotic cell, believed to have been a unique evolutionary event, wherein two simpler cell variants merged, with one cell evolving into the mitochondria. This fusion precipitated a quantum leap in cellular complexity, ultimately paving the way for the emergence of multicellular organisms. Throughout Earth's evolutionary journey, several pivotal moments have shaped the trajectory of life on our planet. Events like the Cambrian explosion, the asteroid impact that wiped out the dinosaurs, and other potential turning points have significantly influenced the development of life as we know it. Earth appears to have navigated these junctures with a stroke of luck, leading to its unique evolutionary path. The rare Earth hypothesis delves into the role luck may have played in Earth's development. Many of the characteristics that make Earth conducive to life and the milestones in its evolutionary history appear to be one-of-a-kind occurrences. According to the weak anthropic principle, these events could be exceptionally rare. Until we gather more evidence, ideally by observing similar events elsewhere or witnessing them occur again, we cannot assume their likelihood. The combination of these improbable factors raises the possibility that intelligent life in the universe is exceedingly rare. This perspective offers a potential solution to the Fermi paradox, suggesting that the apparent emptiness of the galaxy might be a true reflection of reality. It's plausible that we find ourselves on the only habitable planet in the cosmos, gazing out from our extraordinary Earth into the vast, seemingly uninhabited expanse of the universe. Is planet Earth a zoo for aliens? Cosmic quarantine hypothesis. The Fermi paradox raises a perplexing question. If extraterrestrial life is likely, why haven't we made contact with advanced civilizations? One intriguing theory, the zoo hypothesis, proposes that alien life exists but intentionally remains hidden, treating Earth as a sanctuary. But why would they stay hidden? One reason could be a fear of interplanetary contamination, similar to our concerns about microbes from Earth disrupting other planets. Ecosystems. To maintain ecological balance, aliens might observe us from afar, avoiding direct contact. Communication challenges also factor in. The vast differences between species could lead to confusion or fruitless interactions. Therefore, aliens might prefer covert observation to prevent misunderstandings or disruptions to our natural development. Some interpretations suggest that aliens known as watchers passively observe Earth for scientific study or to allow our civilization to evolve without interference. Alternatively, they might monitor without engaging, deeming us too primitive for direct contact. Another explanation posits differences in timescales. Aliens could be visiting Earth infrequently, perhaps every few thousand or million years, leaving no lasting evidence. The slow reveal theory within the zoo hypothesis suggests that a sudden introduction to advanced alien civilization could be disastrous for humanity. Thus, aliens might opt for a gradual approach, allowing us time to adapt to their existence. The lack of contact with extraterrestrial life could be due to ancient taboos among alien cultures, prohibiting contact with less advanced civilizations. This tradition might have originated from a dominant ancient civilization in the galaxy, setting a precedent for younger civilizations. Advanced aliens might only intervene in our development when absolutely necessary to minimize risks in first contact and avoid technological dangers we haven't fully grasped. The preservation hypothesis suggests that civilizations maintain isolation to preserve cultural and technological diversity. Too much interaction could lead to a loss of uniqueness. Cultural factors, like xenophobia or religious beliefs, might also influence the zoo hypothesis dynamics, leading to periods of isolation or unpredictable behaviors in response to cosmic events. Another theory is that intelligent life beyond Earth is extremely rare or non-existent, either naturally or due to a dominant civilization suppressing others. Alternatively, the universe might be a simulation, with Earth as the focal point. Lastly, the laboratory hypothesis proposes that our universe is a controlled environment designed by unknown forces, possibly as part of an elaborate experiment. These perspectives on the zoo hypothesis offer different explanations for the Fermi paradox, providing unique insights into why we haven't encountered extraterrestrial life. Are aliens deliberately avoiding contact with us? Dark forest hypothesis. The universe is vast, with numerous planets that could potentially support life. Despite this, we haven't detected any signs of extraterrestrial life, leading to what's known as the Fermi paradox. This paradox arises from the fact that if even one advanced alien civilization could travel at a fraction of the speed of light, it could have spread throughout our galaxy in a relatively short time compared to its age. Yet, we see no evidence of such civilizations. One possible explanation for the Fermi paradox is the dark forest theory. This idea suggests that while the universe may indeed be teeming with life, civilizations may choose to remain hidden from each other. This caution stems from the competitive nature of life itself. On Earth, organisms compete for survival, resources, and the chance to reproduce. This competition has led to the dominance of certain species, like humans, who have a knack for innovation and resourcefulness. However, this dominance also comes with unintended consequences, such as the extinction of numerous species due to human activities. In a universe where every civilization strives to survive and expand, revealing oneself could be perilous, akin to a lone hunter in a dense, foggy forest, hesitant to call out for fear of attracting unseen predators. Humans, like other beings, form cultures that engage in their own brand of competition. Cultures driven by competition and expansion tend to spread rapidly, often absorbing, dominating, or wiping out others. Our history illustrates this. Humanity poses a threat not just to other species, but to itself. Motivated by our instincts, we've colonized every corner of Earth and are now setting our sights on the cosmos, seeking new territories and resources. It's likely that this competitive spirit isn't unique to Earth, suggesting that an alien civilization that has conquered its own planet may share similar traits with humans, including potential danger. Just as a lone hunter moves cautiously through a dark, dense forest, aware that others like him might be lurking, unable to discern their intentions but assuming they might act aggressively for survival, so too must we approach the possibility of encountering other civilizations in space. This scenario implies that in a chance encounter, taking preemptive action might be a survival strategy. However, this doesn't mean conflict is inevitable. Human progress suggests that we become more peaceful over time. This trend could hold true for other civilizations, where advancement leads to decreased conflict. Alien civilizations could vary from benevolent and peaceful to hostile and militaristic. The crux of the matter in interstellar encounters is the uncertainty of intentions. We cannot easily determine whether an alien civilization is peaceful or aggressive, just as they might misunderstand or distrust our peaceful gestures. This ambiguity presents a significant existential challenge when encountering others among the stars. Moreover, the challenge of communicating with and encountering alien civilizations is compounded by the vast distances of light years, resulting in significant delays. These delays raise uncertainty, prompting consideration of preemptive attack as a potentially safer strategy. This concern is amplified by the unpredictable pace of technological advancements and the concept of gaining an advantage through striking first. Throughout history, technological progress has been pivotal in warfare, often leading to one-sided annihilation. From ancient legions to modern drones and guided missiles, advancements continually outpace previous military technologies. In the context of interstellar conflict, the time it takes to deploy an invasion fleet across light years means that by the time it arrives, it could be outdated. Consequently, wars between civilizations may focus on eliminating the other as an existential threat. The fear of a preemptive strike from the other side could prompt a rapid and overwhelming assault to prevent retaliation or future reprisals. The gravity of such situations allows no room for error. Assuming most civilizations are planet-based, they become susceptible to devastating weapons capable of annihilating entire planets. One such example is the relativistic kill vehicle, a missile traveling at a substantial fraction of the speed of light. A missile of human scale, traveling at 95% the speed of light, would possess energy equivalent to Earth's entire nuclear arsenal. Just a few of these missiles could ensure the destruction of a targeted civilization, with even a single strike potentially being catastrophic. Such weaponry is not beyond the capabilities of civilizations only slightly more advanced than our own. These weapons are particularly menacing because they heavily favor a first strike approach, making defense or countermeasures nearly impossible once launched. Interstellar conflicts could thus be swift and decisive, with the initial aggressor often emerging victorious. This reality underscores the potential existential threat posed by every civilization to others. In a universe like ours, civilizations might fall into two categories: those that remain silent and those that have perished. So, what should our approach be? Currently, it's unlikely that extraterrestrial civilizations have detected humanity. Our radio signals, spanning just a century, have traveled only a negligible distance in the cosmic expanse and have likely dissipated into background noise. At our present technological level, staying unnoticed is probable if we avoid drawing attention and if no one specifically targets our unremarkable solar system. However, as we venture further into space exploration, these questions demand reconsideration. We're uncertain whether we're alone in this vast forest or not. For now, the most prudent path forward is cautious observation. If we detect another civilization revealing itself, our response should be measured and careful, observing from a distance before engaging further. However, it's conceivable that our perspective is clouded by our primitive competitive instincts, which may be painting an excessively fearful picture of potentially predatory alien civilizations. It's plausible that, as a species, we're not yet mature enough to grasp the true nature of the universe. There might await a friendly galaxy for us once we attain that readiness. At present, the imperative is clear. Exercise caution in the signals we transmit into space, keep a vigilant eye on the skies, and deepen our understanding of the galactic forest. Whether this forest is fraught with peril, filled with potential allies, or entirely devoid of other life forms, only thorough observation and study will unveil the truth. Let's hone in on this scenario. In the clearing, the hunter confronts another being, both gripped by fear. In this intense moment, the hunter pauses, taking a deep breath and makes a choice. Perhaps the path out of the dark forest lies in stepping into the clearing together, opting for collaboration rather than confrontation. Can the James Webb Space Telescope find signs of alien life? The James Webb Space Telescope, in less than a year since its launch, has already exceeded expectations with its remarkable images of distant galaxies, nebulae, exoplanet atmospheres, and deep space fields. Its capabilities are unmatched in detail and sensitivity. Now it's embarking on an exciting new task, searching for signs of life beyond Earth. Using its advanced infrared technology, the Webb telescope will closely examine distant planets for chemical signals that could indicate the presence of life, known as biosignatures. This phase of the mission represents a significant step forward in our exploration of the cosmos and our position within it. The Webb telescope has four main methods for potentially detecting extraterrestrial life: identifying essential chemicals for life, detecting substances produced by biological processes, looking for elements necessary for a stable climate, and finding unusual chemical combinations that don't typically occur together. Scientists have primarily focused on studying planets similar to Earth, located within their star's habitable zones, where conditions might support liquid water. With cutting-edge telescopes like Webb, equipped with precise optics and infrared imaging, the focus of exoplanet exploration is shifting from mere discovery to a deeper analysis of their characteristics. This advanced examination involves directly capturing images of exoplanets and studying their atmospheres using spectroscopic data. Since the 1800s, scientists have known that specific chemicals absorb and emit light at distinct wavelengths. By analyzing the chemical composition of exoplanet atmospheres, researchers can gain more insight into their potential habitability. The Webb telescope is gearing up to search for four key chemical indicators in its quest for signs of life: oxygen and ozone, phosphine and ammonia, methane and carbon dioxide, and chemical imbalances. Oxygen is particularly important as a biosignature because of its crucial role in life processes. Earth's history provides a fascinating example. Initially, our atmosphere was rich in carbon dioxide, creating what's known as a reducing atmosphere that hindered oxidization. However, the emergence of cyanobacteria and other photosynthetic organisms gradually transformed this, leading to the Great Oxygenation Event around 2.4 to 2.0 billion years ago. This shift from a reducing to an oxidizing atmosphere played a pivotal role in the evolution of life on Earth, enabling the development of more complex organisms over time. Additionally, the interaction between oxygen and ultraviolet radiation in our upper atmosphere led to the formation of the ozone layer, which now protects life on Earth from harmful UV radiation. However, it's important to note that detecting these molecules in the atmosphere of an exoplanet doesn't guarantee the presence of life. Studies have shown that there are non-biological processes, abiotic processes, that can lead to the creation of oxygen and other molecules in a planet's atmosphere. For example, the runaway greenhouse effect can occur when surface water evaporates, leading to increased heating and further evaporation, creating a feedback loop that can result in significant water vapor in the atmosphere. When exposed to solar radiation, this water vapor can undergo photolysis, breaking down into hydrogen and oxygen gases. In one scenario, hydrogen may escape into space, leaving behind oxygen. Another possibility arises for planets tidally locked within their star's habitable zone. Intense radiation on the star-facing side can lead to photolysis, resulting in an atmosphere rich in abiotic oxygen. Surprisingly, oxygen, essential for many life forms, was toxic to the early photosynthetic organisms on Earth, suggesting that high oxygen levels could impede the development of life. Ammonia and phosphine, naturally occurring in gas giants' atmospheres and their icy moons, are also produced by life on Earth. Phosphine has gained attention as a potential biosignature after its detection in Venus's atmosphere. However, these gases exist in small amounts on Earth, posing a challenge for detecting them in the atmospheres of distant exoplanets. Methane and carbon dioxide are also considered potential signs of life, especially when found together, as they originate biologically on Earth. Methane arises from organic decomposition and digestion processes, while carbon dioxide is a product of respiration in oxygen-consuming organisms. Furthermore, carbon dioxide plays a crucial role in regulating temperatures on a planet. Imbalances in its concentration can lead to extreme climate conditions like a runaway greenhouse effect or glaciation. Finally, chemical imbalances in an exoplanet's atmosphere could indicate the presence of life. Life disrupts chemical equilibrium by consuming certain substances and producing energy and byproducts. This idea aligns with the Gaia hypothesis proposed by planetary scientist James Lovelock, who suggested that true chemical stability is typically found in lifeless systems or planets, using Mars as an example to illustrate this concept. Another potential biosignature not highlighted by Barstow is hydrogen. Recent studies from Cornell University suggest that volcanic hydrogen in an exoplanet's atmosphere might expand the habitable zones around stars. Hydrogen gas acts as a natural greenhouse gas, and volcanic activity is seen as crucial for life's emergence. Additionally, research from the University of Cambridge has introduced the concept of Hycean planets, ocean worlds with hydrogen-dominated atmospheres, as promising candidates in the hunt for extraterrestrial life. However, the presence of these chemicals in an exoplanet's atmosphere should not automatically be seen as proof of life. Barstow stresses the complexity and precision required in exoplanet research. Accurately measuring the quantities of these gases is challenging because their signals can overlap and demand careful separation for analysis. She underscores that the James Webb Space Telescope is just beginning to unveil a vast new realm of planetary atmospheres. Through this exploration, many existing assumptions about exoplanets and their atmospheres are likely to be reassessed or even debunked. Is finding alien life closer than we think? The quest to uncover extraterrestrial life has evolved from questioning its existence to contemplating when it might be discovered, marking a significant shift in the focus of modern astronomy. There's a growing optimism among scientists that signs of life on distant worlds could potentially be detected within our lifetimes, with some suggesting it could happen in the next few years. This increased anticipation is fueled by recent advancements and missions in space exploration. For example, the James Webb Space Telescope has provided promising indications of potential life on an exoplanet. This telescope, along with other missions, heralds a new era in space exploration, one centered around what could be one of the greatest scientific discoveries. Considering the vastness of the universe, with its countless stars and planets, it's logical to assume that Earth might not be the sole harbor of intelligent life. Today's advanced technology and exploration capabilities have brought humanity to a crucial juncture where answering the profound question of our cosmic solitude is more feasible than ever. This current phase in space exploration transcends mere exploration. It's also about the pursuit of discovering life beyond our planet in the vast expanse of the universe. Telescopes now have the capability to analyze the atmospheres of distant exoplanets, searching for chemicals typically associated with living organisms on Earth. A recent example is the detection of a gas on the exoplanet K218b, situated 120 light-years away, which bears similarity to one produced by marine organisms on Earth. K218b resides in the Goldilocks zone of its star, where conditions are just right for liquid water to exist, a critical factor for supporting life. Scientists anticipate confirming the validity of these initial signs of life within a year. The lead researcher from the Institute of Astronomy at Cambridge University suggests that such confirmation would profoundly alter the approach to seeking extraterrestrial life, hinting that life might be more widespread in the universe than previously believed. Even if K218b doesn't yield signs of life, there are 10 more planets in the Goldilocks zone awaiting examination, and each outcome, positive or negative, will provide valuable insights into the potential for life on these worlds. This project is just one of many endeavors aimed at detecting signs of life in the universe, with some concentrating on our solar system and others venturing into deep space. While telescopes like NASA's James Webb Space Telescope boast impressive capabilities, they have limitations, especially in detecting smaller Earth-like planets near their stars due to glare. NASA intends to launch the Habitable Worlds Observatory in the 2030 S, equipped with technology to minimize starlight and analyze Earth-like planet atmospheres. Another significant advancement is the European Southern Observatory's extremely large telescope, to be stationed in the Chilean desert. Its vast mirror will facilitate detailed observations of planetary atmospheres. These advanced telescopes employ a centuries-old technique used by chemists to identify chemicals based on the light they emit, enabling the analysis of light from hundreds of light years away. In addition to examining distant exoplanets, some missions concentrate on the icy moons of Jupiter and Saturn, deemed promising for extraterrestrial life. NASA's Clipper and the European Space Agency's Jupiter Icy Moons Explorer missions are scheduled to explore Europa, one of Jupiter's moons, in the early 2030 ES. Europa, with its subsurface ocean and water vapor plumes, stands as a prime contender in the quest for life beyond Earth. NASA is gearing up to send the Dragonfly spacecraft to Titan, one of Saturn's moons, renowned for its abundance of carbon-rich chemicals and potential for sustaining life. Meanwhile, though currently harsh, Mars is believed to have once harbored conditions conducive to life. NASA's Perseverance rover is collecting samples from a crater that may have once been an ancient river delta, with plans to return these samples to Earth for analysis in the 2030 ES. Beyond our solar system, the quest for radio signals from alien worlds persists, spearheaded by institutions like the Search for Extraterrestrial Intelligence, SETI Institute. The James Webb Space Telescope's prowess in pinpointing promising locations for alien civilizations has reinvigorated SETI's search endeavors, now employing cutting-edge technology to detect potential communications from distant planets. While some scientists maintain skepticism regarding the likelihood of receiving a clear signal from extraterrestrial life, the prospect remains a captivating and unequivocal means of confirming life beyond Earth. The last 3 decades have witnessed a revolution in our comprehension of exoplanets, and the detection of life signs would represent a monumental scientific leap, reshaping humanity's understanding of its cosmic significance. Join us today as we delve into the most intriguing scientific theories about consciousness. Everything from how consciousness can exist outside the brain to if consciousness requires a sense of self to exist, as well as covering phenomena like déjà vu and lucid dreaming and how it can be linked to consciousness and brain function. Let's get into it. Does the human brain create consciousness, or does consciousness create the human brain? The prevailing view among neuroscientists is that consciousness arises from the brain, and there are strong reasons for this belief. Our everyday experiences are closely tied to the brain's function and its complex networks. For example, a significant blow to the head can lead to unconsciousness, a common occurrence among boxers. Damage to the brain's primary visual cortex can result in the loss of conscious sight. Furthermore, changes in the brain's chemical environment, whether due to illness or the use of mind-altering substances, can profoundly alter our perceptions, thoughts, and emotions. Psychedelics like LSD and mescaline, for instance, can dramatically shift experiences, causing anything from intense joy to deep despair. This suggests that our normal state of consciousness is heavily dependent on the brain. However, stating that the brain actually produces consciousness might be an oversimplification. Just because something depends on another doesn't mean it's created by it. Let's consider some analogies. The cool breeze from an air conditioner doesn't originate from the unit itself. It merely cools and filters the air from outside. Similarly, a faucet doesn't create water, it just controls the flow. When we open curtains, light floods the room, but the curtains aren't the source of the light, they simply allow it to enter. These comparisons were particularly insightful to thinkers at the end of the 19th century, such as William James, Frederick Myers, F.C.S. Schiller, and Henri Bergson. They challenged the dominant physiological views of their time and proposed an alternative perspective on the brain's role in consciousness. They introduced the concept known as the filter or transmission theory of brain function, often referred to simply as filter theory. According to this model, the brain plays a vital role, but rather than generating consciousness, it taps into a pre-existing state of awareness. The key ideas here are filter, transmit, allow, channel, select, draw out, constrain, control, shape, and alter, not produce, create, or invent. Supporters of filter theory suggest that our everyday consciousness is supported by a hidden realm or well of awareness. This idea emerged during a time when the notion of a subconscious mind was gaining prominence. Some, like physiologist W.B. Carpenter, viewed subconscious mental processes purely through a physiological lens, calling it unconscious cerebration. Others, however, were more open to the idea that the subconscious might possess its own form of consciousness. Thinkers like William James, Frederick Myers, and Pierre Janet saw phenomena like dual or multiple personalities as evidence of hidden conscious states that exist alongside our primary consciousness. The concept of subliminal or transmarginal consciousness was proposed to explain a wide range of mysterious occurrences, including sleepwalking, hysteria, memory, dreaming, creativity, psychic phenomena, and mystical experiences. While it might seem that subliminal awareness is confined to individual consciousness, evidence like psychic abilities, such as telepathy and clairvoyance, and possibly even cosmic mystical experiences, suggests that it might extend far beyond the individual. To describe these ideas, Edward F. Kelly coined the term roster, or resonant opening to subliminal and transpersonal assets. Although not committing to the full extent of the subliminal, William James referred to the Mother Sea of Consciousness in his 1897 Ingersoll lecture titled Human Immortality, which was a foundational presentation of filter theory. Years later, writer and philosopher Aldous Huxley revived filter theory during the new age of psychedelic exploration through his mescaline-inspired work, The Doors of Perception, where he called it Mind at Large. According to filter theory, our everyday, or supraliminal, awareness arises from the deeper, subliminal ocean of consciousness through the filtering functions of physical matter, primarily the brain and nervous system, along with related psychological mechanisms. These systems act as filters or selectors, allowing certain subliminal elements to become part of our conscious experience while leaving much else unseen. Huxley proposed that the brain and nervous system act like a reducing valve, channeling the vast potential of the mind at large into a more manageable stream. This process of filtering which subliminal information becomes conscious is driven by practicality and survival. Typically, only information that is directly useful or necessary for an organism's survival is selected. Perception is thus narrowed and focused to enhance efficiency. This filtering also serves as a protective mechanism, shielding us from the overwhelming or disturbing flood of possible information. However, when these biological and psychological filters are altered through methods like meditation that quiet the mind, reduced survival pressures, traumatic experiences, or the use of psychoactive substances, content that is usually blocked may enter our conscious awareness. Filter theory, therefore, offers an explanation for a wide range of extraordinary and transcendent experiences. The early proponents of filter theory acknowledged that they were using analogies and metaphors, recognizing that their descriptions lacked specific mechanistic details. Their aim was to provide an alternative view of how the brain and nervous system function, one that didn't rely on the simplistic idea of direct creation of consciousness. While contemporary neuroscience provided little insight into these filtering processes, the theory invited philosophical speculation. When William James introduced filter theory, he placed it within the context of mind-body dualism, suggesting that the physical brain filters consciousness. But his goal was to challenge the dominant dualism that viewed the brain as the creator of consciousness. James was also open to other metaphysical perspectives, such as idealism and neutral monism, which don't draw such a sharp line between brain and consciousness. These approaches potentially bypass the complex mind-body problem, which deals with reconciling the material brain with the non-material nature of consciousness. Henry Bergson further explored this idea in his work Matter and Memory, applying filter theory to the study of perception and memory, as well as phenomena like telepathy and near-death life reviews. His philosophical stance, known as neutral monism, views the fundamental elements of the universe as neutral, not inherently mind or matter. In this perspective, both the brain and the body, like everything else in the universe, are composed of neutral images. perception is the process of selecting certain images over others, with the brain and body themselves being particular sets of these images. Filter theory continues to be relevant today as a philosophical challenge to the simplistic idea that the brain is the sole creator of consciousness. At its heart, the theory serves as a thought-provoking tool that encourages deeper reflection on how the brain functions. However, its importance might go even further. Recent efforts have aimed to revive the insights of filter theorists, integrating them with the broader and more diverse empirical evidence now available to researchers. Some of this evidence comes from the renewed field of psychedelics research, which is experiencing a resurgence for both therapeutic applications and basic neuroscientific exploration after many years of being sidelined. This revival has been supported by legal approvals, marking a significant shift in the study of consciousness and brain function. A contemporary interpretation of how psychedelics work, known as REBUS, relaxed beliefs under psychedelics, shares some similarities with earlier filter theories. Specifically, it suggests that psychedelics loosen entrenched high-level beliefs, such as those related to the self, allowing for an unleashing of upward information flow from the brain's limbic system and other areas. However, REBUS differs from traditional filter theories, which argue that relaxing psychobiological barriers grants access to deeper subliminal awareness. Unlike Huxley's idea of roster, which involves reducing valves and the expansive mind at large, REBUS does not explicitly consider the concept of subliminal consciousness, particularly one that extends beyond the individual's mind and brain to the external world. As a result, there is debate over whether REBUS can fully explain the range of experiences induced by psychedelics, including mystical and near-death-like experiences, as well as parapsychological events. To fully address these phenomena, the concept of mind at large might need to be revisited. How can consciousness exist outside of the brain? Our instincts, honed through evolution, offer us rapid and crucial insights for survival, and these instincts continue to influence us in the modern world. For example, we might have an uneasy feeling about stepping into an elevator with someone we don't know, even if we can't pinpoint the reason behind it. Yet these gut reactions aren't always accurate, especially in fields like science and philosophy, where our evolutionary history hasn't equipped us. Intuition often involves a strong conviction in something's validity without clear justification, a sense that might not align with reality. When we dig into our intuitions about consciousness, we uncover complexities that challenge what initially seemed straightforward. Reflect on these questions and your immediate responses as we explore common beliefs and misunderstandings. How can we detect consciousness in a being such as the human brain from an external perspective? Is consciousness essential for our behavior? Although these questions are interrelated, addressing them individually can offer valuable insights. Consciousness might exist without any visible signs, as seen in locked-in syndrome. This condition, exemplified by Jean-Dominique Bauby, the former French Elle editor-in-chief, leaves individuals fully aware but almost entirely immobilized. Bauby, despite being paralyzed from a stroke, used his blinking eye to write his memoir, The Diving Bell and the Butterfly, through approximately 200,000 blinks. Anesthesia awareness is another case where patients remain conscious but paralyzed during surgery, unable to communicate their awareness despite experiencing the procedure. These extreme situations suggest that consciousness can exist without external manifestations, even in artificial intelligence, which poses challenges for recognizing and understanding consciousness in entities beyond our current grasp. Reevaluate our original question. What signs might indicate the presence of consciousness? Usually, we determine an organism's consciousness based on its actions. Guided by our instincts, we commonly believe that humans are conscious while plants are not. The common belief, backed by both intuition and scientific research, is that consciousness depends on having a brain or a central nervous system. However, the situation becomes more complex when we consider behaviors usually linked with conscious entities, such as reactions to injury or nurturing, that plants also display in remarkable ways. Despite this, we often conclude that plants exhibit these behaviors without experiencing pain or affection, implying a lack of consciousness. In What a Plant Knows, a field guide to the senses, Biologist Daniel Chamovitz explores the fascinating ways plants react to external factors like touch, light, and temperature, showing similarities to animal responses in similar conditions. For example, vines change their growth patterns when touched, seeking out structures to attach themselves to, while the Venus flytrap distinguishes between inanimate objects and potential prey, quickly closing its trap on the latter. Chamovitz explains that when plant cells are stimulated, they produce electrical signals similar to those in animal nerve cells, involving intricate interactions among ion channels and other cellular mechanisms. Additionally, he notes genetic parallels between plants and animals, indicating that some genes responsible for light detection and response in plants are also present in humans, influencing various biological processes from cell division to immune responses. Chamovitz's work also examines plants' abilities to sense sounds, smells, their environment, and even hints at a form of memory. Although plants' mechanisms may resemble those of animals, the prevailing scientific view maintains that plants lack consciousness as we understand it. For instance, memory in plants, defined as the ability to form, retain, and recall information, can be observed in phenomena like the Venus flytrap, which only closes its trap after receiving 2 separate touches on its sensory hairs, suggesting it remembers the initial stimulus. Similarly, wheat seedlings exhibit a form of memory by recalling cold conditions they endured, which is essential for their subsequent flowering and seed production. Interestingly, some plants that face stress can produce offspring that are better equipped to handle similar challenges, suggesting a form of transgenerational memory, a phenomenon also observed in animals. Ecologist Suzanne Simard has made significant strides in forest ecology with her research on mycorrhizal networks, complex underground fungal systems that enable plants to exchange nutrients and information. Her work reveals intriguing relationships, such as the support exchange between Douglas fir and paper birch trees, and the preferential care that Douglas fir mother trees provide to their own offspring. This complex interplant communication resembles an Earth's natural internet, yet it does not necessarily imply consciousness, particularly in terms of having subjective experiences. Similar questions arise in the realm of advanced robotics and artificial intelligence. For instance, an AI designed to comfort a person or an algorithm predicting search queries may exhibit behaviors that seem sophisticated but do not imply consciousness. The complexity behind these functions is due to intricate programming rather than any form of self-awareness. This leads us to ponder whether consciousness is essential for specific behaviors or if it suffices for a system to convincingly simulate these actions. The real challenge is differentiating between authentic conscious experience and sophisticated yet non-conscious programming, a distinction that remains difficult to pinpoint as both conscious and non-conscious entities can demonstrate behaviors typically associated with emotions or cognitive states. Our initial reactions to identifying consciousness are now being questioned, prompting a deeper inquiry. Does consciousness play a critical role in or influence the physical system it inhabits? One could theoretically carry out all actions and thoughts without conscious awareness, similar to an advanced robot's operation, though this idea is hard to fully comprehend. David Chalmers. Philosophical zombie thought experiment captures this concept, inviting us to imagine a person who behaves exactly like anyone else externally but lacks any internal subjective experience. The notion of philosophical zombies has ignited considerable debate, with philosophers like Daniel Dennett arguing that such a scenario is implausible. Dennett suggests that consciousness is fundamentally linked to the operation of a human brain. Considering the possibility of zombies among us compels us to critically assess our assumptions about consciousness and how it manifests. By envisioning situations where individuals display behaviors associated with consciousness, such as showing concern in emergencies without actually feeling it, we are led to question whether consciousness is truly necessary for these actions. This thought experiment not only challenges our views on human behavior, but also broadens its impact on our understanding of consciousness in the natural world. When we observe non-human entities displaying behaviors similar to those of humans, like a starfish maneuvering around obstacles despite lacking a central nervous system, it calls into question our assumptions about consciousness in living systems. The philosophical zombie scenario exposes the limitations of our intuitive understanding of consciousness. It highlights that the distinctions we make between conscious and non-conscious beings based on their behaviors may not be as robust as we think. By metaphorically taking off our glasses, we recognize that our deeply held beliefs about consciousness and its connection to certain behaviors may require reassessment, encouraging a wider view of consciousness across both human and natural contexts. Does consciousness require a self? We often see ourselves as the conscious observers, the ones who perceive and experience the world. As we shift our gaze from one object to another, it feels as if we're situated inside our own heads, behind our eyes, directing our awareness to notice things consciously. This deeply ingrained belief about the mind has influenced both scientific and philosophical explorations of consciousness, leading to misunderstandings about the nature of experience. The conscious self is imagined not as the physical body, but as a sort of internal observer, the you, who is listening to these words right now. Although consciousness is indeed a feature of our physical being, it is not the same as the conscious entity we perceive within our minds. The concept of a conscious entity has ancient roots in scientific thought, notably with René Descartes. Descartes viewed the natural world as devoid of consciousness, attributing awareness to humans due to a separate, transcendent entity that could illuminate our understanding. However, introducing such a conscious entity only shifts the problem of explaining consciousness. What makes that entity aware? If it is inherently conscious, then consciousness itself remains an enigma. If it is not inherently aware, what triggers its consciousness? Another entity within it. This reasoning leads to an endless regress, leaving the mystery of consciousness unresolved. Daniel Dennett refers to this issue as the Cartesian theater. Scientific theories on consciousness often propose a self-like mechanism within the brain that imparts the quality of awareness to the brain's processed information. The brain operates as a hierarchical network, with sensory inputs processed at lower levels and advancing through various stages of cognitive processing. Some theories argue that consciousness emerges from a bottom-up process, arising spontaneously from the brain's activities. Others suggest it is a top-down phenomenon resulting from reflective thinking in the brain's higher regions. The brain's organization ensures that sensory information is processed primarily in the posterior regions, while decision-making and attention are managed by the frontal areas. Research into the neural correlates of consciousness in both the front and back of the brain supports both bottom-up and top-down models. A significant challenge emerges because the frontal areas of the brain are active during communication. When participants share their conscious experiences in experiments, it's difficult to determine whether the activity in these frontal regions is linked to their role in consciousness or simply a result of verbalizing those experiences. A recent study tackled this issue by interpreting subjects' experiences through physiological signals like changes in pupil size, which reduced reliance on verbal reports and thus minimized the involvement of frontal brain areas. This approach suggests that the neural mechanisms tied to a self-reflective state might not be central to consciousness itself, but rather play a role in conveying conscious content. Furthermore, phenomenological research indicates that the self may not be essential for experiencing consciousness. People undergoing meditation or psychedelic experiences often find themselves in states of awareness without a distinct psychological self, yet consciousness persists. These states imply that consciousness exists independently of an experiencing subject, representing a kind of unstructured awareness where experiences, including the self, emerge. In this view, consciousness is the space in which the concept of a psychological self can appear, rather than something owned by the self. In a conscious system, forming basic beliefs about the world is possible. Here, belief means the simple ability to perceive and understand certain attributes, such as recognizing the characteristics of a red apple. This perspective resonates with Immanuel Kant's notion that we never directly perceive reality, but encounter representations of it. Our consciousness shapes how we perceive these representations. Bayesian inference, which deals with updating beliefs based on new information, reveals a challenge. The brain cannot account for every possible cause of each piece of evidence. Carl Friston's free energy principle introduces the free energy minimization approach, which helps the brain refine hypotheses about sensory input by accounting for unexpected evidence. thus aligning beliefs more closely with reality. Moreover, this principle sheds light on how we interact with the world. Active inference involves creating a hypothesis about how the world should be different from its current state, such as the intention to move from sitting to standing. The brain constructs a belief about standing and then takes action to align the actual state with this expectation, ultimately achieving the desired posture. Anil Seth's beast-machine theory posits that the persistent experience of a unified self is a Bayesian belief sustained through the reduction of prediction errors. This mechanism supports and reinforces the belief in a continuous, integrated self. If we assume that consciousness necessitates complex cognitive processes for introspection, we might conclude that only humans or similar beings possess it. However, if consciousness is more fundamental and simpler than the concept of self, it implies that consciousness might be more widespread. By discarding the idea of the self as a prerequisite, we can view consciousness as a basic, inherent ability rather than a product of advanced reflective thought. Can higher dimensions solve consciousness's hard problem? In the rich realm of philosophical inquiry, Heraclitus's quote, "The waking have one common cosmos, but the sleeping turn aside each into a cosmos of their own," provides a profound entry point into examining the elusive link between consciousness and physical reality. This investigation requires moving beyond traditional philosophical frameworks, delving into speculative territory that explores the nature of space and its relation to awareness. This journey, which embraces transformative perspectives, aims to unravel the cosmic enigma of the mind-matter connection by breaking down space into its various forms and considering its implications beyond the conventional three-dimensional understanding. Central to this philosophical exploration is the Cartesian split, which views matter as extending through space, while consciousness or the mind is seen as lacking spatial characteristics. This division not only underpins the scientific perspective of nature as a mechanical construct, but also sets the stage for William James's critique of Cartesian thought. James disputes the idea that experience is without spatial extent, arguing instead that mental phenomena possess spatial qualities. In his earlier work, The Spatial Quale, he demonstrates how spatial attributes are not confined to the external world but also permeate our imaginative experiences. Our philosophical journey thus navigates two distinct yet interconnected types of space: physical space and sentient space. Physical space refers to our shared external reality, whereas sentient space encompasses individual experiential realms, including imaginative spaces, hypnagogia, psychedelics, and dreams. Bertrand Russell and Alfred North Whitehead contribute to this discussion by highlighting the divergence between perceived and material spaces, suggesting a complex relationship that extends beyond mere physical dimensions. The notion of dimensions extending beyond the familiar three plays a crucial role in this philosophical exploration. Hyperspace emerges as a possible framework for grasping the elusive connection between mind and matter. By invoking Leibniz's idea of infinitely many spaces and worlds coexisting without physical distance, we open the door to a multidimensional universe where mental and physical realms might intersect. The more broad Smithy's theory introduces a groundbreaking perspective in this context, proposing that mental and physical phenomena could coexist within a larger, multidimensional space. This theory challenges traditional dualism, emergentism, and idealism by envisioning a space that integrates both the common and individual cosmoses. It suggests that imagined and physical realities are not separate entities, but converge within a grander spatial framework, potentially offering a fresh approach to the mind-matter dilemma. Exploring these philosophical dimensions prompts profound questions about reality, consciousness, and the nature of the cosmos. By venturing into dimensions beyond our immediate perception, this inquiry not only questions our understanding of space and sentience, but also invites a re-evaluation of our foundational worldviews. Speculating about a unified space where mind and matter merge hints at a cosmos where the distinctions between internal and external, mental and physical, become fluid rather than rigid. This speculative journey through the realms of mind, matter and space reveals a universe far more intricate and interconnected than traditionally thought. By moving beyond existing concepts and embracing the potential of multidimensional spaces, we gain a glimpse into a reality where the cosmic puzzle of consciousness and the physical world may one day be solved. It serves as a reminder of the boundless mysteries at the core of existence, urging us to continue our pursuit of understanding with an open mind and a spirit of adventurous speculation. Is consciousness the collapse of the wave? Function? Consciousness, central to our sense of existence, is the gateway through which we interpret reality, formulate thoughts, and feel emotions. While it is the very essence of our being, its complete understanding remains elusive, despite extensive exploration across various cultures and intellectual traditions. Delving into consciousness reveals a rich array of perspectives, each shedding light on the nature of reality, our own essence, and the complexity of the universe. On one side of the debate, consciousness is seen as the fundamental fabric of existence, with the material world merely a reflection or projection of this deeper reality. This view resonates through numerous spiritual and philosophical traditions, proposing that consciousness itself is the true essence of the universe, with physical phenomena being secondary or illusory. It envisions a cosmic harmony where consciousness orchestrates material occurrences. In contrast, some skeptical viewpoints suggest that consciousness might be an illusion, a mere byproduct of neural activity without genuine control or real experience. This perspective portrays human existence as a passive experience, where consciousness merely observes rather than directs, echoing T.H. Huxley's idea of us as helpless spectators. This stance questions the role of consciousness in shaping reality, envisioning a mechanical universe where consciousness is a byproduct rather than a driving force. Another notable viewpoint compares the brain to a computational system, drawing analogies between mental processes and the evolution of information technology. From ancient metaphors of memory as wax impressions to modern comparisons with computers and digital networks, this analogy reflects our effort to understand the brain through the lens of technological progress. Critics, however, argue that while this computational model helps map non-conscious processes, it fails to capture the subjective depth and essence of consciousness. This raises important questions about the relationship between algorithmic functions and the qualitative nature of conscious experiences, highlighting a gap in our understanding. Exploring the quantum dimension, Roger Penrose's theories offer a groundbreaking perspective that links consciousness with fundamental aspects of physics. Penrose's objective reduction theory proposes that consciousness arises from quantum mechanics, specifically from the collapse of the quantum wave function where the quantum and classical realms intersect. This theory provides a scientific framework for consciousness and attempts to solve the measurement problem in quantum mechanics, suggesting a universe where consciousness and quantum phenomena are intimately connected. In collaboration with Stuart Hameroff, Penrose developed the orchestrated objective reduction theory, which suggests that quantum vibrations within brain microtubules are crucial for orchestrating consciousness. This theory compares consciousness to a cosmic symphony, where quantum processes in the brain's microtubules are essential for generating conscious experience. Although initial skepticism focused on the difficulty of maintaining quantum coherence in the brain's warm, moist environment, recent research supporting quantum states in microtubules has renewed interest in this quantum approach. This view proposes that conscious experiences emerge not only from complex neural networks, but also from deeper quantum processes that interact with the fabric of space-time. This perspective envisions consciousness as a fundamental feature of the universe, extending from the microtubules in neurons to the vast cosmos. Light, particularly organic light, plays a crucial role in this discussion, potentially serving as a link between the brain's quantum activities and the universe's consciousness-infused structure. The connection between light and consciousness has been symbolically and literally significant throughout history, from the divine auras described in ancient texts to the illuminating experiences reported by mystics, suggesting a deep and pervasive link between light, life, and consciousness. The narrative also revisits the universe's beginnings, underscoring the pivotal roles of light and organic molecules in the rise of life and consciousness. The examination of the primordial soup and the self-organizing nature of organic molecules suggests an inherent inclination toward complexity and consciousness, challenging the traditional notion that consciousness is a recent development in evolutionary history. Instead, it envisions a universe where consciousness, shaped by quantum processes and the fundamental properties of light and matter, has influenced the cosmos from its very inception. This broad inquiry into consciousness, bridging philosophical perspectives with quantum theories, prompts a re-evaluation of our cosmic position. It proposes that consciousness might not merely arise from complex biological systems, but could be an intrinsic aspect of reality, deeply integrated into the universe's essence. Viewed through this perspective, the quest to understand consciousness transforms into an exploration of the universe's profound mysteries, presenting a cosmos where consciousness serves as both the creator and the creation, weaving together the fabric of existence. Does the brain hallucinate conscious reality? Your account of losing and regaining consciousness under anesthesia vividly highlights the elusive and puzzling nature of consciousness. This temporary state of non-awareness underscores how crucial consciousness is in shaping our sense of reality. When consciousness recedes, so too does our perception of self and the world, pointing to the fact that our grasp on what we call reality is deeply tied to our conscious experience. The marvel of anesthesia, its power to momentarily halt consciousness, touches on one of the most intriguing puzzles in both scientific and philosophical realms: how consciousness emerges from the physical processes within our brains. In this intricate dance, billions of neurons collaborate, not just to create any form of consciousness, but to produce the distinct personal experience of I that each individual possesses. This complexity raises fundamental questions. How do the physical interactions of neurons give rise to the subjective nature of consciousness? Why does our conscious experience have the qualities it does? And how does it arise from the otherwise non-conscious physical world? Your exploration of consciousness, its link to intelligence, and its potential in both living beings and artificial entities invites profound contemplation. You astutely separate consciousness from intelligence, suggesting that consciousness is more fundamentally related to our existence as living beings, rather than our cognitive functions. This distinction is vital in understanding why advanced computers, despite their growing computational abilities, might not achieve consciousness. Consciousness could be a fundamental aspect of biological life, shaped by evolutionary forces and the need to interact with complex environments, a notion supported by ongoing scientific investigations into consciousness. The idea that consciousness could be a form of controlled hallucination is particularly intriguing. It implies that our brains, enclosed in the darkness of our skulls, are constantly making predictions about the external world based on scant sensory input. These predictions, or best guesses, construct our perceived reality. This concept not only clarifies how we build our immediate experience, but also how this process can be tricked, as seen in optical illusions and altered perceptions. Furthermore, it suggests that our sense of self, the coherent identity experiencing these perceptions, is itself a construct, a narrative the brain creates to interpret the sensory data it receives. The rubber hand illusion and its variations vividly demonstrate how flexible our sense of self and body ownership can be, revealing that our brain's perception of our own body can shift with changes in sensory input. This adaptability also applies to how we perceive our internal state, which our brain constantly monitors and regulates, often without our conscious awareness, except when something goes awry. This ongoing internal regulation, vital for our survival, suggests that the essence of consciousness is deeply intertwined with the biological needs of life itself. Your investigation raises an important point. Grasping the nature of consciousness might require a paradigm shift, from seeing it as an enigmatic and almost mystical phenomenon to recognizing it as an emergent result of complex biological systems. Just as the quest to understand life evolved from searching for a vital force to exploring it through the principles of chemistry and physics, our understanding of consciousness may similarly advance. By dissecting how the brain produces our experiences and sense of self, we can demystify consciousness, making it a phenomenon explainable through brain and body interactions rather than an unfathomable mystery. This perspective shift has significant implications for fields like psychiatry and neurology, opening new paths for diagnosing and treating disorders related to consciousness and self-perception. It highlights both the uniqueness of human consciousness and its place within the broader spectrum of life, reminding us that our experiences represent just one manifestation of consciousness in the natural world. Your reflections, which blend personal experience with scientific insight, encourage a deeper contemplation of the links between our sense of self, our view of reality, and the biological processes that underpin life. This perspective challenges us to expand our understanding of consciousness not as a separate phenomenon, but as an essential component of the living world, shaped by and shaping the evolutionary journey of life on Earth. Could psychedelics help quantify our waking state? Consciousness is often defined as the state of being alert and aware, setting it apart from unconscious states like deep sleep. However, some researchers are delving into how the nature of conscious experience can be dramatically transformed, particularly through the use of psychedelic substances. These drugs can alter a person's perception in profound ways, leading to rich, detailed, and intense experiences. This line of research not only aims to expand our understanding of consciousness, but also explores potential therapeutic applications for various psychological and neurological issues, suggesting that psychedelics may tap into fundamental aspects of consciousness. At its core, consciousness encompasses our ongoing experience of existence, extending beyond mere wakefulness or sleep. It includes both our typical state of awareness and altered states. For example, Chris Timmerman's research uses psychedelics to investigate changes in critical aspects of mental experience. This method is akin to tossing a stone into a placid pond and watching the ripples spread out. In everyday life, our perception molds our reality. During psychedelic experiences, this perception can shift dramatically, as evidenced by experiments with DMT, where users report entering vividly real, alternate dimensions. Modern neuroscience proposes that our perception of reality is a form of managed hallucination, where our brain creates our version of the world. Psychedelics might provide insight into the brain's processes for crafting both extraordinary and everyday experiences. Timmerman's research focuses on DMT, a compound found in various plants and a principal component of ayahuasca, a traditional Amazonian brew known for its transformative effects. DMT's value in research comes from its ability to consistently produce profound shifts in reality perception within a short time, making it ideal for study in controlled settings like MRI scanners to track brain activity during these experiences. The renewed interest in psychedelic research has attracted participants like Shamil, a seasoned meditator interested in consciousness and the self. His involvement in DMT studies at Imperial College London's Centre for Psychedelic Research included being scanned before, during, and after DMT sessions. These studies have revealed intense sensations, visual fractals, and a sense of physical boundary dissolution, resulting in highly detailed geometric patterns and experiences beyond ordinary description. Analyzing these experiences alongside changes in brain activity has shown alterations in brain oscillations associated with different states of consciousness. Specifically, DMT appears to decrease alpha waves, which are usually present during relaxed states with closed eyes but no vivid sensory input, while increasing delta waves, which are linked to dream states. This suggests a detachment from external stimuli and a creation of rich, internal realities. Chris's research employs functional MRI to investigate how DMT affects specific brain areas and networks, providing evidence for the idea that consciousness may function as a kind of controlled hallucination shaped by hierarchical brain systems. Psychedelics appear to disrupt these hierarchical structures, offering the brain a chance to explore new models of reality with an immersion similar to our everyday experiences. By understanding how these substances alter the brain systems involved in consciousness, there is potential to develop innovative treatments for mental health conditions marked by persistent, negative thought patterns, such as depression and anxiety. Psychedelics could facilitate more adaptable mental frameworks, potentially breaking cycles of negative thinking and fostering healthier mental states. Moreover, DMT's potential extends beyond its therapeutic uses to serve as a valuable research tool, offering opportunities for personalized mental health strategies and deeper insights into the nature of consciousness. This line of inquiry not only aims to address immediate health concerns, but also to explore fundamental questions about human experience. Is consciousness a continuous stream or a series of discrete moments? The investigation into whether our awareness functions as a continuous flow or in discrete, intermittent bursts is a deep dive into the essence of consciousness. This question goes beyond simple curiosity about perception mechanics, tapping into a long-standing philosophical and scientific debate. The idea that consciousness is a seamless, uninterrupted stream, a story that never pauses, challenges modern cognitive science and revisits the discussions of ancient thinkers. Traditionally, consciousness has been viewed as a continuous flow shaped by our personal experience. From waking to sleeping, it seems like a steady stream of perceptions, thoughts, and feelings. Yet this intuitive sense is complicated by insights from both ancient traditions and contemporary neuroscience. St. Augustine, an early Christian philosopher, explored how we perceive the passage of time, past, present, and future, within a single moment of awareness. Similarly, the Abhidharma tradition in Buddhism proposed that consciousness is not a smooth continuum, but a series of discrete moments, each a fleeting experience followed by the next. These ancient ideas resonate with modern research, particularly in cognitive neuroscience. A notable study from the Laboratory of Psychophysics at the École Polytechnique Fédérale de Lausanne has revitalized the discussion by suggesting that consciousness incorporates both continuous and intermittent elements. Their model posits that consciousness isn't a constant stream, but is made up of brief, distinct intervals of awareness, interrupted by periods of unconscious processing. This perspective implies that our brains continuously analyze and integrate sensory information in the background, even when we're not consciously aware of it. Supporting this theory, experiments show intriguing results. For instance, when participants view overlapping lines or a series of colored discs, they perceive a unified image rather than separate stimuli. This suggests a delay of around 400 milliseconds between the actual stimuli and conscious perception, indicating that consciousness lags behind real-time events due to rapid, unconscious processing. Similar effects are seen in auditory and tactile perceptions. For example, the rabbit illusion, where sequential taps on the arm are felt as a continuous stroke, demonstrates how the brain constructs a sense of continuity from discrete inputs. This phenomenon further supports the notion of intermittent consciousness. The implications of these findings are significant. Our perception of a continuous reality is actually a construct of the brain which pieces together discrete moments of awareness. This intermittent nature of consciousness enables swift, unconscious processing of sensory information, allowing the brain to create a coherent narrative from fragmented experiences. This process is crucial for navigating dynamic environments and forms the basis of complex human cognition and our perception of the world. The dual-phase model introduced by researchers compares the interaction between conscious and unconscious processes to the communication between a ship's captain and the engine room. This analogy provides a metaphorical framework for understanding how our brains manage the flood of sensory input. According to this model, unconscious processing is crucial, with consciousness appearing not as a continuous flow, but as episodic highlights that direct our actions and perceptions based on the complex processing happening out of our awareness. This modern viewpoint not only challenges our conventional ideas about consciousness, but also connects ancient philosophical inquiries with contemporary scientific research, revealing the intricate and fragmented nature of our reality. Thus, the exploration of consciousness remains at the cutting edge of human knowledge, where the enigmas of the mind are continuously explored through philosophy, psychology, and neuroscience. What is hypnagogia? The state between wakefulness and sleep. If you've ever experienced the jarring sensation of falling just as you're drifting off to sleep, causing a sudden awakening, or encountered this feeling as you're about to wake up, you're not alone. Approximately 70% of people have felt this. Known as a hypnic jerk, this phenomenon occurs during the intriguing transitional period from wakefulness to sleep, called hypnagogia, which often includes peculiar hallucinations. For a long time, the nuances, origins, and effects of hypnagogia remained underexplored, leaving many psychologists and neuroscientists perplexed. However, recent research has begun to illuminate the mysterious aspects of this dreamlike state. Researchers have worked diligently to unravel the nature of hypnagogia. One study describes it as a common and benign mental state that people frequently experience as they transition between being awake and falling asleep or waking up. This phase involves notable shifts in mental processes, resulting in brief sensory episodes or hypnagogic hallucinations that occur spontaneously and vary in intensity. Research suggests that about 85% of these hallucinations are visual. Approximately 35% involve tactile sensations within and around the body, and about 20% are auditory. Unlike other sleep-related phenomena such as dreams, parasomnias, or sleep paralysis, hypnagogia represents a distinct and typical type of hallucinatory experience. Despite the seemingly surprising fact that up to 70% of people might encounter hallucinations during the pre-sleep or waking moments, these experiences are often mundane and straightforward, and many individuals may not even recognize them. Findings from the Journal of Sleep Research indicate that hypnagogia encompasses a wide range of hallucinatory experiences, varying in frequency, nature, triggers, and effects. Visual hallucinations are the most commonly reported, presenting in various forms such as abstract shapes, patterns, or vivid imagery. These visuals can differ in color, ranging from black and white to vibrant hues, movement, static or dynamic, and spatial quality, flat or three-dimensional. The Tetris effect, named after the popular video game with geometric shapes, illustrates how repetitive tasks before sleep can influence visual impressions. For instance, avid Tetris players might visualize the game's pieces aligning in their minds, similar to how chess players in the Netflix series The Queen's Gambit might mentally rehearse chess moves. This effect can also apply to sensations related to routine physical, auditory, or tactile activities. Auditory hallucinations during hypnagogia can include isolated sounds or accompany other sensory experiences, ranging from soft murmurs to loud crashes. Common auditory hallucinations involve familiar sounds like ringing phones or doorbells, and brief snippets of speech leading to hypnagogic speech, which might sound like mumbling during sleep. Reports of hypnagogia frequently include experiences across various senses, such as tasting unfamiliar flavors, detecting distinct odors, or sensing shifts in temperature. Some individuals also encounter somatic illusions, such as feeling a sense of floating, numbness, or altered body perception. However, the most commonly described hypnagogic phenomenon is the hypnic jerk, a sudden startling sensation of falling. Research indicates that susceptibility to hypnagogia varies among individuals, often linked to sleep quality and various health conditions. Those with compromised sleep due to insomnia, PTSD, depression, or anxiety are more likely to experience these states. Additionally, individuals with a strong belief in the supernatural have also been found to be more prone to hypnagogic experiences. Despite its association with poor sleep and mood disorders, hypnagogia is recognized for its potential benefits, particularly in enhancing creativity and problem-solving. According to research in the Encyclopedia of Creativity, hypnagogia allows for the examination of hallucinatory imagery while it is still present, which can be particularly useful for solving problems. Historical figures such as Auguste Kekule, Beethoven, Salvador Dali, and Isaac Newton have credited hypnagogia as a source of inspiration for their creative work. This suggests that the hypnagogic state may be a fertile ground for generating innovative ideas and solutions that are less likely to emerge during other sleep stages or while fully awake. The Journal of Sleep Research also highlights that hypnagogia can be deliberately induced, with hypnosis being a practical approach. The recommended method involves relaxing the major muscle groups for 30 minutes, followed by 20 minutes of indirect hypnotic suggestions. This ability to purposefully induce hypnagogia not only expands the horizons of sleep research, but also offers a way for individuals to harness their creativity and problem-solving skills more effectively. Deliberately inducing hypnagogia could be a fascinating and enjoyable endeavor, providing a unique opportunity to explore the benefits of this transitional state of consciousness. In this liminal zone between wakefulness and sleep, hypnagogia reveals itself as a complex and intriguing phase, rich with unusual hallucinations. When intentionally induced, it holds the potential to become a powerful tool for enhancing creativity and innovative thinking, making it a compelling area for further exploration. Can lucid dreaming help us understand consciousness? Waking from a nightmare can be a startling shift, transitioning abruptly from a vividly imagined threat to the tranquil surroundings of our bedroom. This stark contrast highlights a profound insight into human consciousness. Our perception of reality, whether in dreams or during waking moments, is a creation of our minds. Lucid dreaming, where one becomes aware of and can control their dreams, offers a compelling way to explore this concept. It provides a tangible experience that the reality of dreams can be as immersive and detailed as our waking life. This isn't just an abstract idea, it's a deeply felt experience for those who have delved into lucid dreaming, myself included. The fascination with lucid dreaming is evident in public interest, such as the ABC Nightline feature on Stephen LaBerge, a psychologist who has developed methods to induce these states. Accounts from individuals like Chris Moss vividly illustrate the intense realism of dreams, fueling curiosity and encouraging others to explore lucid dreaming. This exploration isn't just about the novelty of dream control, it also holds significant implications for understanding consciousness. Lucid dreaming reveals that our brains have an astonishing ability to create intricate, immersive worlds without any external sensory input. This internal generator crafts experiences that can feel as real and coherent as those from the physical world. This realization blurs the line between waking and dreaming states, showing that both are constructs of the brain, though with different limitations. While waking life is continually informed by sensory data and grounded in a shared external reality, dreams are only limited by our imagination, free from the sensory constraints of our waking experiences. The implications are significant. Philosophers and neuroscientists like Thomas Metzinger and V.S. Ramachandran propose that consciousness, whether in waking or dreaming, is essentially the same, a virtual reality created by the brain with the self as a participant. This view suggests that what we perceive as real is actually a sophisticated model crafted by our minds, so convincing that it seems indistinguishable from reality. Recognizing that our waking experiences are also a form of virtual reality does not diminish their importance. Rather, it deepens our appreciation for the mind's ability to construct our perceived reality. Lucid dreaming vividly illustrates the boundless potential of the human mind, showcasing its remarkable adaptability and inventiveness. It offers a rare chance to delve into personal exploration and self-understanding, pushing the limits of our perceived reality. Engaging in lucid dreaming not only enhances personal insight, but also prompts us to reconsider our beliefs about the nature of reality and our role within it. This practice reveals that our conscious experiences are subjective constructs rather than direct reflections of the external world, which can challenge our certainty and encourage us to embrace new perspectives. There are also ethical considerations linked to this realization. The way we engage with constructed environments, whether they're virtual worlds created through technology or the ever-shifting landscapes of our dreams, can reveal and shape our character. Although our actions in these realms might seem to lack tangible repercussions, they impact our ethical self-conception, testing and revealing our values, empathy, and reflective capacity. In essence, exploring lucid dreaming broadens our grasp of the mind's potential and questions our fundamental beliefs about reality and identity. It compels us to rethink the nature of experience, knowledge, and existence. By acknowledging the constructed nature of our perceptions, we are encouraged to approach life with a fresh sense of wonder, curiosity, and humility. Lucid dreaming, with its vivid and adaptable qualities, serves as a powerful metaphor for the human condition. We are both the creators and inhabitants of the worlds we experience, constantly balancing between perception and reality. How does déjà vu relate to brain function and consciousness? Déjà vu, a French phrase meaning already seen, is a captivating and enigmatic experience that many of us encounter at least once. It manifests as a sudden, eerie sensation that an ongoing event or experience has occurred before, despite lacking any concrete proof. Charles Dickens vividly captured this phenomenon in David Copperfield, describing it as an intense yet elusive flashback to an unplaceable past. This brief but striking feeling often leaves people bewildered, marveling at the strange familiarity of a new situation, a paradox that has fascinated scientists and philosophers for ages. The allure of déjà vu spans various fields, including neurology, psychology, and even the mystical. Research indicates that about 1/3 of people have experienced some form of déjà vu, underscoring its widespread occurrence across different cultures and experiences. This phenomenon isn't limited to a mere sense of recognition. It can also encompass a range of sensory experiences like sounds, smells, and tactile sensations, adding to its complexity. Arthur Funkhauser has explored the nuances of déjà vu by categorizing it into 3 distinct types: déjà vécu, already lived; déjà senti, already felt; and déjà visité, already visited. Déjà vécu, the most frequently reported type, involves a vivid and detailed sensation of reliving a moment with a sense of knowing what will happen next. Déjà senti, in contrast, is a mental experience where a thought or feeling seems oddly familiar, lacking the spatial or temporal context. Déjà visité pertains to a spatial sense of familiarity with a place never before encountered. These classifications provide insight into the varied manifestations of déjà vu and suggest that it might stem from different neurological or cognitive mechanisms. Numerous theories attempt to explain the origins and mechanics of déjà vu, with various researchers putting forth intriguing hypotheses. One leading idea suggests that déjà vu arises from a disruption in the brain's sensory integration, where a fleeting piece of sensory input, such as a sight, sound, or smell, induces a vivid and immersive recollection of a past memory, blurring the line between past and present. Another possibility points to a malfunction in the brain's memory system, where information skips the usual transition from short-term to long-term memory, creating the illusion that an experience is much older than it truly is. Additionally, some propose that a slight delay in cognitive processing might be responsible, where the brain processes information with a brief lag, resulting in the uncanny sensation of experiencing and recalling an event at the same time. In addition to neuroscientific explanations, psychoanalytic and even parapsychological perspectives offer alternative insights into déjà vu. These range from the idea that the subconscious mind is fulfilling unspoken desires to theories involving past lives and reincarnation. Although these viewpoints lack the empirical evidence found in scientific research, they enrich the diverse array of theories exploring the mystery of déjà vu. Central to the phenomenon of déjà vu is the role of the self in these episodes. Many accounts include a heightened sense of conscious awareness during the event, implying that déjà vu might not be a passive experience, but rather involve an active engagement of the individual's sense of self. Some people even report being able to deliberately recall the feelings and imagery linked to déjà vu, suggesting that these experiences could offer more than transient moments of confusion. They might serve as portals to deeper explorations of consciousness and memory. Investigating déjà vu extends beyond mere academic curiosity. It holds promise for uncovering more profound insights into human memory, consciousness, and identity. By delving into déjà vu, researchers and theorists explore the complex landscape of the mind, aiming to understand how we construct reality, how memory and perception interconnect, and how our sense of self is shaped by our experiences. Despite the difficulties inherent in studying such a subjective and elusive phenomenon, the quest to understand déjà vu reflects our enduring drive to grasp the mysteries of our existence and expand the boundaries of knowledge about the human mind.